So last time where we left off, we had the entire robot assembled, like you can see here, and we also had it standing. So now the legs can move. We have power for all the Arduinos, and it can kind of like stand on its own, right? And then we started to get very confident, and we tried a few things, and we even tried to, kind of like get on 3 legs. And before we knew it, we actually fell to the ground. Now, when we fell to the ground, I noticed later on the video that we actually broke one of the shoulders. So this is the box that holds 2 of the servos, and this is the shoulder joint. This connects to another servo to actuate the shoulders like this. Now the thing is, when you manually over torque this past a limit, the way this meets the servo, this is basically pressed onto the servo pinion. So it's like a little gear. It's a gear with little teeth. And so this is just plastic, so you can really over torque it, and that's what happened when it fell. So I had to replace this entire part, which is fine. But while I was replacing it, I also, took the liberty to redesign it a little bit. I didn't record it because it was really small stuff, but you can see here that, we got rid of this cutout here, which was leading to a lot of support material on the 3D prints. We might bring it back, I'm not sure. And I also added a small FR here, a letter, so you can tell which side of the robot this part goes on without checking CAD. Just you can read it here. FR means front right. And we also made this mating surface a little thicker. Like we increased the interference to 0.2 millimeters, so it's like a tighter fit. So hopefully it won't strip again. And and so overall. And then I also got rid of the cutout to remove the support, like I said. But I also have this thing where it's like, I feel like ideally, if someone's looking at this robot dog for the first time, they just see a dog. They don't see, a bunch of electronics and it's a robot and it's complicated. No, they see a dog and it's friendly, and we should get to the point where it's so good that maybe you don't even know it's a dog. Maybe it's just it's an animal, it's a Pokemon, it's something that exists. So I do have a thing about hiding electronics and hiding the motors and not showing them. So that's also why I closed it. That's also why I want to get rid of the screws, because screws they're not electronics, but screws are not as natural as some of the other surfaces in here. So I do want to get rid of those too. But anyway, so that was one of the latest improvements on the leg. And you can see here what the latest iteration of a leg and shoulder looks like compared to the previous one. Like, for the OGs, the green stuff, that was the first leg, and it's like very shaky, and the tolerances are not good. A lot of rattles, a lot of play on the shoulder, even when the servo is not actuating. So it's getting better, still more room for improvement. Now, the reason why I only changed one shoulder, not all of them, is because we're also running out of filament. So I've ordered more filament, still not here. So we're kind of like out of filament. We cannot make any big changes right now. The other thing is, like, when the new filament comes in, we're not working on orange anymore. We're now working, I think, on blue. And so we're gonna have, we're slowly replacing from green to orange to blue. And I feel like that'll make the videos more entertaining because you can tell, how things are changing. I do hate to have a mismatched color robot, but that's another story. What else was I gonna say? So because we couldn't make any more changes to the hardware, I was starting to move on to the software side of things. So our stand last time was a little rigid. The legs were like these, and it was like almost felt like it was on tippy toes. So I started playing with the knees and bending a little more. I was kind of looking like how dogs look like when they're standing, especially the rear legs, and got to a place where it was okay. Nothing to show because, again, it's just standing. But what did happen was the cables, this mess here, started smoking. So on the previous video, I mentioned that powering these through jumper cables is really a really bad idea, just because of the amount of current we're pulling, and we don't have enough copper here to handle basically the heat. I said that, and then I did nothing about it. I was like, yeah, we'll upgrade it eventually, and I did not upgrade it. I did nothing. We continued running, and guess what? It happened. It melted. So you can see here that these wires, the connector is completely melted. it's a ground. Well, actually the positive also melts here on the back converter. So out of the back converter, both here on this side and on the bus bar side start to melt. Obviously these are the wires where this is exactly where we expected these to fail. The wires don't fail. These ones didn't fail at the wire themselves, they fail at the connector. That makes sense because they're probably crimped, and that's like where there's like the least surface cross-section area where the heat's gonna melt the material the first. And so, yeah, once you start to see some white smoke, it's actually a plastic that starts to smoke first. Once you start to see that, you wanna shut it down right away because, you know, if those break and your battery shorts, it could burn basically anything there. So I'm not powering it anymore, and so for that reason, I can't do any more software development either. The good news is that I did come up with a plan for replacing these and upgrading these, and I've already ordered the parts, and they won't come here till I think it's Wednesday. They won't come in till Thursday, so maybe tomorrow or Friday. We'll see how things go. So I'll walk you through right now what we're gonna change on the computer. But on the meantime, I was thinking we could fix this mess of wires. Like, this looks terrible. So I was hoping we could fix that. And also for today, I wanted to use the little filament that we do have left to try to print a leg with no screws. So we're gonna remove all screws of this leg. This is gonna be 3D printed joints, no screws. This should require no installation other than, you know, the 2 screws to connect it to the servos, which I cannot get rid of, but everything else will be one part, or at least printed as one part. So we'll try that. So first I'll explain how we're gonna mitigate this situation where our wires are getting so hot that they melt. Second, we're gonna clean up this electrical mess. We're gonna improve the packaging. We're probably gonna, I don't know, add a level here to the torso or something crazy. I haven't thought about it too much. And third, we're gonna make a new leg with no screws. So let's get to it. 3 things for today. Just gonna keep it very short. So to do today, first, explain electrical improvements or the plan improvements. Second, repackage electricals in the torso. And third, build a single piece leg. We're gonna call these mono leg, as in mono as in one. As in, yeah, right? As in mono, as in, wait, am I getting this wrong? How do you say mono as in singular? Let's add ChatGPT. Always knows ChatGPT. Mono, in the sense of singular, is just mono, and it comes from the Greek prefix mono, which means one or single. Okay, so we're right. Okay, I am building a robotic leg that is made of one piece. What would be a clever name for it? Mono leg? Let's see if AI can do better at naming stuff than we can. Monolegs works, but if you're looking for something a bit more flair, you could go with monolimb or unileg. Monolimb. Solus leg for a sleeker. No. Oh man, no. Monoleg. We're building a monoleg. Anyways, I guess the other thing that happened off camera, and I just didn't include it because it's kind of boring, but so I started mapping some of the components that we added. This is the Arduino Uno. I didn't have to cut this one. This one you can get on the Arduino website. This is a back converter, which I found on GrabCAD. This one I did have to model from scratch, which is the bus bar here. And basically I just take calipers and measure it. Pretty straightforward. And then this is the battery, the LiPo battery that we need to somehow we need to fit all that stuff in there, which is a little comedic. And of course, in the future, there might be an AI controller versus a Raspberry Pi 5 with a AI hat, but and a camera and all this stuff. We're not doing that right now. Yeah, just to quickly cross point number 1 here, explaining the electrical improvements. So this is what our electrical layout looks like right now. I'm just gonna add a tag here. This is B1. Okay, and so this is B2. So what the issue here is the cables that connect the bus bar to the back converter here, right? So right, so what we need to do is we're gonna upgrade these cables. Actually, jumper wire. I wonder what's the gauge on these jumper wires. So it's 28 gauge. Okay, so I'm gonna make a note here. Upgraded buck converter to bus bar wires from 28 gauge to 16 gauge. And we're gonna explain what this means in a bit. So that's one change we're making. So if you don't know, so gauge basically is when it comes to like the thickness of a lot of metal stuff, it's usually in gauge, and it's not in like, you know, it's a wire, so we could talk about diameter, and yes, you could equate these gauges to diameter. The way I understand this is we're talking gauge because it has to do with pressure. Actually, that is true for sheet metal, where there's sheet metal gauges. I don't know if that's the case for wire. Let's look it up. Okay, the gauge, the American wire gauge, originated in the number of drawing operations used to produce a given gauge of wire, right? So they basically, a drawing operation, they're not drawing with a pencil or something. They're basically pulling a piece of metal through kind of like a die, a draw plate, to make it thinner, right? And the more operations, the smaller the wire, and the higher the gauge, right? So a 28 gauge wire, like these jumper cables that we're using here, is thinner than a 16 gauge wire, which is what we're upgrading to, which is closer to what we have here. And of course, you know, I think they're referring exactly to the copper part of the wire and not the insulation around it. But yeah. Okay, the other thing was that we're adding a switch. And well, let me just show you what I bought from Amazon. So this is the entire Amazon order. So we have switches here, which I didn't model and we need to. Right now, the way you turn on and off the robot is basically unplugging the battery. This isn't great because the XT60 connector is actually there's a lot of friction. So if you really want to turn it off really quickly, because you know there's an emergency, that's not a great way of doing it. Also, if we eventually package the battery somewhere deeper in the robot, somewhere inside, it might be super inconvenient to reach the battery. So a switch that's from the outside might be way cleaner. So I ordered these. These look pretty simple switches. You know, basically the way this works is they have two terminals on the back side, negative, positive, and so you route these to one of the cables going into the buck converter. Into or out to? I think into is fine. Yeah, probably into to minimize the current. Well, actually, I'm not sure. So these are rated for 20 amps at 12V or 120 volts, 10 amps. So I am slightly worried that eventually we might be maxing those out. This doesn't mention if this is continuous current, you know, and so on, or spiked. But yeah, this isn't ideal. But I would say it was kind of hard to find a beefier switch on Amazon. So we're adding that. We need to put that on CAD also. I haven't added this on CAD yet. Next, some spools of 16 gauge wire. Like I mentioned, 16 gauge, it's thicker than the existing 28 gauge wire. And we can look here, gauge current. So you can see like a table like this. Let's see if there's a nice one here. That's not nice, but you can see here for a gauge, for example, we just got 16 gauge. The diameter is 1.29 millimeters, right? Cross-section area 1.31 millimeters square. You know, you have the resistance per 100 feet, in this case 4 ohms. Ohms per kilometer 13. Maximum amps for chassis wiring. I don't know what that means, what they mean by chassis wiring. They're rated at 22. You know, 22 maximum amps for power transmission, 3.7. You know, I assume the difference here is that power transmission is constant, so 3.7 amps constant, and chassis wiring is not constant, so 22. And then we compare it with what we had previous, 28, where like the maximum amps for chassis wiring was 1.4, and for power transmission was 0.2, right? So we're increasing from 0.2 to 3.7, so more than 10x, more than an order of magnitude. So I think, you know, that will make me sleep better at night. Didn't really do a lot of math on these, primarily because we don't know much about the servos. You know, kind of like that's what happens when you buy hobby grade from AliExpress. You really don't have a lot to go with. You kind of like have to experiment a little bit. I have no power supply to experiment with. Maybe that's the next thing to get. But I feel like we're being safe here. You know, as long as the servos are not like stalling all the time, you're not pushing them to do a lot of things. Again, I feel like this is pretty small robot dog. But if we run into any more issues, I will put down the hammer and get some equipment. The other thing I got here was a joystick. So I was looking for an analog joystick. Turns out you can buy these PlayStation 2 controllers, like super old joysticks. I guess they made a ton. There's a room in China with a bunch of them, but these are analog 2-axis controllers. And so bought this pack, which comes with 5. I'm starting to think how we can control the robot, and I think you know it's like dogs have like a leash, right? So I was thinking like we would have a leash, and at the end of the leash a joystick so you can drive it around. Now, of course, we do have a lot of degrees of freedom in this one. We can go front, back, left, right. We can rotate, but it can also kneel. So I don't know if... So those are a lot of things to pack into one joystick. Especially, you cannot pack all of that into one 2-axis joystick. But I thought maybe 2 joysticks. I know it might get tricky. But, you know, if we can move forward and backwards for the time being, I would be happy with that. And then we can iterate on that. I also got another Arduino, just because once we have our Arduino in here, if we need another Arduino during assembly just to initialize things, it's very annoying to have to take apart the Arduino in the robot, especially because you already have all the wires in place. Yeah, so wiring is a mess. Don't want to make it more of a mess. So yeah. Also, to simplify Arduino operations, I got a USB extension cable, just so, you know, I think right now, like this is the Arduino cable we have, right? So when you're, you know, figuring out how to teach a robot to walk, you need to have your computer right next to the robot, which is, it's super, like this is not long enough to get out of the reach of the legs, you know, so the legs can basically hit your computer as you try to program it. So that'll fix that. I got some wire labels just because like all the servo wires look the same, and I don't know which one is which one's right, which one's left, which one's front, rear, shoulder, knee, hip. I don't know, so we're gonna label that. And then the last thing here is I got connectors. So these are lugs and different kind of connectors you can put in the wires. So right now, for example, these wires here are shoved into the buck converter, and these have clamps and I just screw the hell out of them. But sometimes these will, like if you shake it a lot or pull it, they will come off. So really what you want is a ring that will go around the screws on these buck converter terminals, and it will be super safe, or safer than these. And then you want to repeat that for all your critical connections that should never be coming off, like probably anything bus bar related, where coming off means like it's a terrible short. There's things that we could do for the servo connectors to make them tighter, but so far none of them have come off. So and anyways, I also got a wire crimper for those connectors. So when you buy connectors for wires, you also need a crimper. This basically ensures that, yeah, it's like pliers that are sized perfectly for the connectors. So when you put the wire and the connector together and you crimp it, it's perfectly snug. It's like the right, basically the copper in the connector deforms the right way to raise the wire in a very good way. The ghetto, like the super sketch way of doing these would be to just use pliers, but no, I know better than that. Yeah, so that's it. Okay, so I'm gonna cross these. And yeah, like I said here, yeah, we added these electric components. I think I said that, right? Yeah, like yeah, the battery, Arduino Uno model, the buck converter model, the busbar model that I modeled myself. We're missing the switch. We need to add the switch. And just gotta think of how things are gonna be packaged in here. We obviously don't have enough room. So let's do that now. Now in real life, I did kind of like started to fit things together, and I did notice that you can kind of fit the Arduino Uno and the buck converter decently. It keeps falling. Decently in between the servos here. Now it's a question of where the busbar goes. The busbar, of course, has so many wires. Has 28 wires coming in of it. So that's 28 wires that it goes somewhere. The routing should be clean. And we also need to add a switch. The switch should probably be close to the buck converter. So maybe on this side here. And of course, we also need to hold the battery. And so I was thinking we could go down here or we could go up. Yeah. Oh, and the other thing was that these Arduino, the USB connector thing here, it's this silver thing here. It's like facing the side wall, so we can make a little hole for it on the side. And so you can come to the side and just kind of like plug your Arduino connector through here. And yes, it's kind of like on the way of the leg, but just be careful, you know. Yeah. So something along those lines. Let's get on CAD. All right. So I'm gonna start the battery. I want to leave for later. I do think we're gonna add a second level on the bottom here, this nice flat surface, and that's where we're gonna add batteries and bus bars. That's what I'm thinking. And then switch on the side, USB on the side. Oh man. And I also would like to put some cutouts here to route the all the wires coming out of these servos. Right now they're kind of like floating in here. We should route them through here and keep them nice and snug. So that's another thing. So maybe we start there. All right, so we're gonna roll back this mirror somehow here. All right, and so what I'm picturing, obviously we want to, why are we, we want to make a routing thing, but we don't want to add more support. Unfortunately, I think we're gonna have to add some support here if we want to make it look nice. I think if we didn't want to add any support, we could make this a circular cutout, and it will probably minimize how much support it needs. But on the other hand, the issue with that is that wait, where is this going? What, really? So the issue, oh, okay. The issue with that, with circular, is that it just doesn't maximize for the area available, right? Like we could package more if it wasn't for such a small cutout. Nice one. Okay, I'm a little off here. I think we said our walls are gonna be 3. So you could imagine that would be the cutout here, and so round edges, so there's no sharp corners that hurt my wires. Something like that, right? You could imagine something like that. And that is more than plenty for the like for what the servos need. Yeah, something like that. And we don't only need it just there, we also need it on the sides. And you can also always check CAD, but when you can access things in real life, I find it way better there. So these 2 wires would have to get into this wall here. Yeah, maybe right in the middle will be here, and then route it there. That makes sense. Yeah, and so without turning this into Swiss cheese with a bunch of holes, let's add some see, maybe these ones we do make circles. I'm just a little worried. There's a fly flying right in front of my monitor, asking to get killed. Okay, that might be too big of a circle, but let's go with vibes here. Really going just with vibes. So far, vibes taking us pretty far. I'm sure eventually we'll reach the limit of that. That is probably okay. For actually, we can just measure. We can measure. The servo connectors are 7.6 millimeters by 2.6 and 7.6 by 2.6. So as long as the diameter is more than that, so maybe like 12 diameter would be just fine, and we'll just route 1 at a time. Or maybe we have 2 of them. 2 of them, because there's 1 at the front and 1 at the back, the way the servos are coming out. What do you think? Yeah, I agree with 2 of them. Okay, so 2 of them. Something like this. 2 of them 20 millimeters apart, 30 millimeters apart. 40 millimeters apart. Yeah, something like that. Oh, gotta add it to our extrusion. Yep. Something like that. And I guess we can add some chamfers to be extra nice on our wires, right? Because we don't want wires to get hurt. You're seeing those pink strips here because like my chamfer is too big for it to exist on both sides. Smaller chamfer fixes that issue. So something like that. So I think that will do it. And since we went with circles there, we could probably increase this radius for the aesthetic. Okay, yeah, something like that. I'm also surprised we didn't add a fillet. Oh, sorry, a fillet here. And this is one of the good parts of recording everything I do here, because maybe I can go back and see. Maybe there's a reason why we didn't do this before. It just seems like 3 points for structural. So we'll add that. That's some 3 points there. Actually, around everything, man. Yeah, everything. 3 points. Okay. And yeah, we are saying that chamfers are good for the cables, so we should add chamfers there as well. All right. So something like that. And now we can roll back these to the mirror thing. And then we have a front part. And if we go to the top assembly, wherever that is, it's become my thing here has become a mess. I don't know if I'm doing something wrong. Or if that's just how it goes on shape, but anyways, that would be like how it looks. I still think they're a little big, these circles. 12, yeah, I mean, we do know for a fact they're big. We're gonna make them smaller, and yeah, we're gonna make them smaller. These are down to 10. All right, that will do. Again, can't be having Swiss cheese, you know? Can't be having too many holes. All right. So I think that looks better. All right. Cool. Well, actually, I should have made a list of things here. Servo routing. Oh, I want to call this done. Oh, my keyboard doesn't want to write. I think I'm out of battery. It's possible. Servo routing, done. Arduino, packaging, buck converter, packaging, busbar, packaging, battery, packaging, and the switch packaging. All right. Okay, so next let's move on to the boards. So Arduino and the buck converter. So for that, we need to do some fun mates here. So we'll do a planar mate, parallel mate, parallel mate. This and this is parallel. Yes, perfect. Now, no one said you have to be right there, but it is parallel. In theory, you can be parallel and not be touching it, right, Arduino? I don't know why my Arduino board decided it wants to. Okay, perfect. I also needed to not be at an angle. Man, like, this is by no means the best practice for modeling stuff. I am by no means following good standards here. I'm just moving quick, and that's what we do here. All right, so we were talking about how we could make it, we could have this USB thing poking out of the wall. maybe it'll be flush with the wall, you know? So maybe this can be a, what do you call that? A planar mate. Like that. So now it's flush with the wall. Okay, and I kind of like want this to be like symmetrical, right? Right in the middle. But oh, also the other question is like, how far does this need to be from the quote-unquote ground? I guess that's plenty already. I am trying to make this symmetrical. Okay, there's no symmetrical. Okay, let me take some notes here. So actually, let me go to the bathroom. I'll be right back.
A few moments later.
All right, let's take some notes here. We're just gonna do, it's kind of like a bit manual here, but so the Arduino holes are roughly 3 millimeter. So we're gonna screw that down with M3s. So we have 4 holes. So okay, 3 millimeter holes. I like the front ones because they look roughly symmetrical, and parallel axis distance is completely off, 227 millimeter. Although I might not have enough decimals here. Okay. And this position is constrained because we know how far we want to be from the wall. So actually, let me go ahead and let's open the torso and maybe we can modify this part. So what I was thinking, it will be kind of like, so there are the holes here. It will be kind of like this. It's like these boss features, basically. That's what we would call them. And we know they're aligned here. And we're gonna make these. We're gonna make these equal just to save time. Also equal. We know we're gonna nail that down to with M3. So I'm gonna make this 2.8. It's kind of like snug for an M3. And the walls, we're gonna go for 2 millimeters, just random. It's not crucial or anything. So we could be, this could be a line here. I see the issue. It's easier. It might be easier if we align the Arduino somehow. Let me see what mates OnShape has. There is no mid plane mate or anything like that. Do we have a mid plane? We don't even have a mid plane. We could do math here. So 2.6616 on this side. And 2.424 on that side, 2.4424. Doing some math here, that adds up to 5.04. So to make it symmetrical, it will be 2.52 on each side, right? Whoa, sorry. So now with that information, we could do an off, I think like a planar mate with an offset. And I don't know, is there a cleaner way of doing this? I would have done a mid-plane mate in SolidWorks, but oh my god. But I haven't seen something like that on OnShape. Okay, so now that's centered. I am trying to figure out, I'm trying to decide if it's a terrible idea to put this here since the leg is there. But we don't have any other options, cannot be on the front. And to be on the down or up, we would have to put this at an angle. I do like the sound of like, you know, having a USB-C port coming out from underneath or something, like an umbilical cord, but no. So we're gonna keep it there for now, but just putting it out there. I have a feeling that I might regret these. Okay, and we were modifying this part. I don't know where my sketch went. I know I had a sketch. Where did my sketch go? Did my sketches not save or something? That's kind of funny. Man, I had a sketch. Okay, anyway, it's not a big deal. We'll start the sketch again. The good news here is this time around we can actually trust the holes here. So if you remember, it was a quick sketch like this. Basically, it's like basically a two cylindrical features with a hole in the middle that's just for a screw, and they're all the same. Oh man. See, Onshape, when you click multiple elements on Onshape, it's like if you're clicking shift without having to click shift. They all kind of like stay. And clicking escape does nothing. So, you know, that's interesting. And then 2.8, no, just here 2.8, and then yeah, see, that's the same thing. It's like a sticky thing, I guess. It's actually very annoying coming from SolidWorks. 2, okay. And then the thing is, now we can use the holes on the Arduino model to position this correctly. Something like that, and oh, that's a wrong hole. Wait, is it? Oh, I guess these holes are not in line. Fun. Okay, it's kind of like a pokey-yoki thing, I guess. Can't assemble it incorrectly. Well, if that's the case, then I'm just gonna do all the holes in one go. So I'm gonna add for 2 more of these things, since we have four holes. Following convention, we probably will not screw all of them down because that's a lot of screws. Although I didn't mention these, but I did figure out, I did get a really good electrical screwdriver, and it's been a lifesaver. So okay, here, in there, one more. There's an incorrect mate here already, so just get rid of that. Okay, perfect. So now we can mate these two just like that, and use these new sketches. Oh my god. Basically, yeah, use all these sketches to create these tower features, these boss features. And then the question is how tall, but man, Onshape. Yeah, the question is how tall. Whatever we had before seemed to work pretty good, and it's probably kind of shallow, so like something like 5. And with that, we go back to the top assembly here, and basically create a mate with those components. Man, I really hate how it missed here the face. I'm gonna fix that. Yeah, Onshape just has all of these different kinks that gotta just work with. Nope. Oh, it's just not gonna do it, huh? Interesting. Okay, not sure how to work around that one. Oh, I guess we can delete the face. We can try delete face here, and it should complete the circle. And it completes the circle. All right, that's one way of doing it, just not clean. eventually, if you add a lot of features, these will slow down everything. But okay, let's make these and see if there's any issues. The only possible issue is interference with the pins on the bottom side of the board. But that's how it would look, and it's probably fine. Yeah, so it's flush here, and it's very sturdy. So let's run a quick section view, make sure nothing's broken. See, like these kind of pins here, for example, that's interference, I think. And just looking at the board in real life, it does look very tight. Honestly, that seems like a design flaw from Arduino. And it's only on that pin there. It's only on that one. The other ones are fine. Although that seems kind of tight. Also tight in real life, but okay. So let's make these walls thinner. Start there, and then we'll see if we need more desperate measures. 1 millimeter isn't bad. Yeah, see, like, so that fixed a lot of our issues here. And there's no interference with the ribs. That seems fine. Okay. Let's continue working this way. There's more holes. Okay, that's the other holes, and those are easy. Okay, cool. I think I did notice one of the features here is broken, this one here, because this doesn't clash anymore, so we don't need the delete phase anymore. So we can just remove that. And then just for like good practice, we can add some fillets here. We don't have to. We won't. Okay, let's not go there. And I think we'll have enough threads here. So this is 5 millimeters long. For sure, we have enough threads. Yeah. All right. So basically, now we repeat the same thing with the back converter. And it does look much cleaner already. The back converter does not want to be close to the wall. In fact, it wants to be as further out as possible. Mainly because our new wires, the 16 gauge wires, and the wires that we currently have to the battery are thicker, and so they bend less. And if you bend them more, it's gonna put more stress on the terminals for the back converter, which is not good. So ideally, we're trying to maximize the room for that. And we don't know where the battery is going to be or the bus bar is going to be yet, so it's kind of hard to tell which side is ideal. What I can tell you, just like by looking at the back converter in real life, is that it basically does need to fit this way. And like the other orientation, if you rotate it 90 degrees in your head, does not work at all. Like this, it does not work whatsoever. It's actually this that's probably ideal. And then I guess the other thing to keep in mind is that technically, you know, there's heat sinks here for a reason, because it gets hot. Yeah. So either fit it here or try to fit it down here. And if we fit it down there, what else could fit in here, right? Can the battery fit in there? I don't think so, not really. And the bus bar, probably not, just not a good candidate, just because bus bar has so many wires coming out. So I think it does need to fit in here. All right, let's make it fit in here. So the same thing as before, a bunch of parallel mates. Probably one of the more boring parts. Okay, so something like that. As usual, we have the whole question of how to make it mid-plane. There's no good, I haven't found a clean way of doing that. You see, in CAD, it looks like, oh, there's plenty of room. Of course it fits. And I don't know why it's kind of crooked. Oh, the whole robot's kind of crooked. We'll fix that. We'll fix that at some point. Yeah, it looks like there's a lot of room, but I'm telling you, the wires coming out of here and here are not super flexible. And I imagine the battery will be underneath, so they actually will probably need to go down. Again, imagining, because none of these exist right now, but it's not like probably a bad idea to put the battery on top of the heat sinks, right? Doesn't like getting hot either. So it's probably gotta go here somewhere. Like gotta go down here somewhere. The other thing to keep in mind is that the battery on its own, I think it's probably the heaviest component we have. And we do want a weight distribution that's roughly equal across all legs. When I pile the things on top and the robot is standing, it's kind of like unstable. It does rock between legs, especially if you have. Well, it does rock between legs. That's just what happens. So, anyways, let's put this down here, and we'll just split the clearance even on both sides, and let's see if that works. So it was same as before, 1.64. I'm gonna write this down. Very methodical approach. And probably something like that here. So if we measure the distance to the wall here to the PCB, we have JK that did not measure anything. If we measure again, we have 12.295, and hopefully it will be a nice rounded number on the other side. It is 12.175. So we add those two, 12.715 plus 12.295. I must have done something wrong. 12.175, 24.47. So we split that clearance between the two, and that'll give us something that hopefully will work. Planar here. Offset 24.272. So that's what that would look like. And these are M3s, 3 holes, 3mm holes. So yeah, I think we can make that work. Okay, so moving on. Torso. Okay, the back converter is way off here for some reason. There's literally no reason for the back converter to be up here. Let me refresh, see if that works. just a classic on-shape issue. Okay, that's, oh no, just as bad. Okay, so maybe we add another temporary mate here, just for now. Just like offset it like 5 or something. And it should be fully well, that's the wrong 5. Somehow it's always the wrong direction. And flipping the primary axis you would think works, but it doesn't do what you think it does. So actually you gotta switch this to -5, which is not great. So all right, it's still just floating around, you know. Cool. All right, so we cannot do the same, I guess, can't do the same thing we did before, but let me try something else. Maybe these holes here are spaced out evenly. Yes, they are. So we have 39 millimeter. We're gonna call that transpody, and then the other way we have 54, but that's clean. Bilateral. 54 bilaterals. Okay, that's very clean. Okay, now the question is how far to the wall here. 13.735 to the wall. And yeah, and with that we can just, I'm actually gonna just delete all of these mates here. And I'm just gonna directly add these features to the torso, since on-shape's not working. And so same as before, same geometry. This time around, the back converter chip looks way simpler on the flip side. So I think we can go with thicker walls and not interfere with any pins or anything. I'm not gonna measure. I'm just kind of like eyeing it out. Seems fine, you know. We'll do 1 just to be safe. So same thing here, 2.8s. Uh, 1 millimeter walls all around, and then this is a square. Well, sorry, a rectangle. And these are constructions. Yeah, just define some parameters here, make sure it's horizontal, vertical. It'll keep it so you don't have to dimension everything. And then here we know that this is the transbody thing I was talking about. 39, and then bilateral 54, and then to the wall it was like 13.735, and then we said we obviously want this centered, so we can make this a middle point, and that's basically it. And so now we can go back and, well, that's it. 5 will probably do. Now, if we wanted to be fancy, we could write here Arduino and buck converter, but the patterns are so different that these things will only fit one way, right? So I would think there's like no way to mess this up. You never know, but it'll be hard to mess it up. All right, now we can use our cylindrical mates to position this correctly. I like how everything shifts on shape as you're setting mates, and then once you set it, it goes back in place. It's just to like gives you a small heart attack. All right, so now these are our boards. I think this looks clean. So what's left is, well, actually, let's see. So let's cross things out, or at least Arduino is crossed out, buck converter crossed out. So bus bar, battery, and switch. So I guess the bus bar is next, and it's the only place you can go is on the back side here. Now, the funny thing is that we cannot add any features here on the same way we did on the back side, because, well, I guess if we really wanted to, we could, but no, actually we can't. We can't because this needs to be completely flat, because this is what goes against the bed. If we were to print it any other way, it would lead to a lot of support. And this board here cannot sit flush here. I didn't model this perfectly, but there's actually a ton of pins here. So this cannot rest flat against any surface. So we're likely gonna have to add another part here. And you know, if this were a dock, this would be like almost like the ribs. So maybe we'll give it some circular shape. And in there we can have bus bar and battery. This smells like a Chinese factory. Yeah, so we can have bus bar and battery there. Bus bar is a pretty inert component, right? Once you set it up, you should probably, you should never have to touch it again, assuming nothing comes out. Battery, on the other hand, you do need to move all the time. You need to charge it. You need to make sure it's not doing anything suspicious. The other thing to keep in mind is that, yeah, the back converter needs access to both the battery and the bus bar, and the Arduino needs also access to the bus bar, and all the servos need access to the bus bar. So if we put it back here, we do need a lot of space to route cables through it. So these pockets here that are empty will likely be openings to send wires down there. And then we also need an opening here and an opening here for the power cables. Actually, let's add those openings right now. Let's see if oh my god, look, why is this floating here? It's like it has the model, the assembly in context, but it has it on an outdated context for some reason. Okay, maybe later, I guess. Okay, so yeah, for the bus bar here, yeah, we need to add a new part. Like I said, it's like ribs. I'm trying to figure out, and you can see here that whatever part we add, it's likely gonna collide with the legs at some point, unless we're careful about it. So we're losing a bit of range of motion. We have a ton, so it's not a big deal. We could also make it very small. We could make it just like a enclosure down here. But like I said earlier, it's like the whole point is to make it not feel like a robot, and you want an organic shape, right? So you wouldn't want a flat surface with a rectangle on top. That would be the least organic thing you can do. So not that. Oh, by the way, the other thing I was gonna add here, actually no, never mind. I was gonna say, like, because we did buy those joysticks, and we do want to make it so you can control this from a leash, but the leash needs to connect to something, and we have nothing right now. And also the other thing is, like, if we put some ribs here and we get rid of this flat surface, right now the way I've been like testing the robot was by putting a box down here, and it rests on the flat surface, and then you can move the legs without touching the ground. So if we get rid of this flat surface, we will have nothing. So maybe we will want some anchor points on the ends, so we can, like, using rope, we can kind of like lift it on the air. That's one way of doing it. I'm not sure what would be other way of doing it, but that's definitely one way of doing it. So for that, lifting anchors, we could just have holes on the two ends here, and you know, assuming everything is perfectly balanced, weight distribution wise, symmetrical left to right, then that'll work. Big assumption, but that might work. And you know, those would be pretty small holes, like it's just for a string. So that's one way of doing it. Now, if we're putting a hole there, we could also make it a hole for the leash. Now, dogs are usually leashed by the neck on the front, but see, I think that's adding too much complexity for now. Let's just minimize the iteration steps here. But I do think that having a flat surface where you can do things without getting destroyed is important. So for now, I'm just gonna add some holes, front and left, on this part here. So we can, if needed, we can just kind of like hook it off the ground through some strings. I don't have string, so yeah, so always something simple, something like we go here, backside, like something super simple, basically that. Here, construction, and yeah, maybe like 5 millimeters, okay, maybe like 8, and then like 20, something like that. So there's enough clearance to the wall so this doesn't absolutely collapse. Something super simple like that. Does feel a little big, right? So we'll go smaller. And then we'll do the chamfers. All right, something like that. Yeah, I'm gonna add this here to a list of what are we calling this? Holes. Hoist holes. Done. Hoist. I think that's the word. Hoist. Yeah. Perfect. All right. So back to the bus bar. Yeah, we're gonna have something like that there. So we're working on the torso. So let me go to the torso file here. Let me see what planes we have. We have, okay, that's a decent plane. So this is kind of like along the lines of what I'm thinking. We would basically extend these chamfers here. I don't know if this is the most organic shape I've ever seen, but extend, oh. Yeah, so extend the chamfers like that. And we could try to get rid of the chamfers. Chamfers are there for clearance to the legs, so it's kind of like pretty crucial chamfers. It's giving it some Star Wars look here. We could, and this would be a separate part. 50 here. No, 60. At least something along those lines here. I think I need to import, yeah, I need to add this part. Insert torso. I didn't name the part yet, so. Yeah, so it'll be like, something like that. It's not terrible. We could extend that a little bit more. And the battery would also need to fit in there, which actually will not fit in it right now. So it will need to grow. I mean, obviously, the obvious thing to do here is to measure the battery. So then on the slimmest, the narrowest is 38 millimeters. So if we make these like 42 or something like that, I think, well, you need to account for the wall thickness, but yeah, it would have to be like 45 here to account for the wall thickness, or make the wall thinner. So it has to be something like that. And yeah, it starts to look very big. On the good bright side, this is flat, so we still have a flat surface where you can rest. And then we also said, and yeah, you could see like the bus are being mounted there and plenty of room for the wires. We did say that the battery should be easy to access from the outside because it needs to be recharged. So we would need to have an opening on one of these walls. I'm gonna go to the bathroom, I'll be back.
So much later that the old narrator got tired of waiting and they had to hire a new.
All right, I'm back. Yeah, so something like that. Need to figure out how to attach it. Obviously adding more parts, not ideal. So we want to adding more weight also. So we want to make sure this is as good as possible. We probably don't need this top wall, right? It's redundant with the bottom wall there, I think. And then we can mount these down here. Although it is a question of how are we going to make this accessible from the outside. So we're seeing an opening for the battery. That's a pretty, like if we just add a small bulkhead here, that's kind of tight. Also, how do you even access it? I guess you have to flip the robot on its belly. By the way, I noticed that this is actually, everything that is packaged here is now below the walls of the torso. So we could now add something on top to cover everything. But anyways, yeah, so we can have that here. You know, what would be cool is that this entire kind of like triangular structure is like a hatch. And so there's like a hinge on one side and you can just open the entire belly. That would be cool. And we can probably make that happen, just 3D printed hinges. Doesn't have to be a hinge though. What if it's just like snap-on features? It would be nice to make it flush though, make it blend in really well. Also for ease of assembly, like I said, 28 wires that need to go from here to this side. So, I mean, hopefully you do that once and forget it, but don't want to spend a whole day just doing that, so. Wait, let's get the battery in here. Get a sense of what we're dealing with here. Yeah. Okay, so the bulk of the space is the battery, and it would have to go in the middle. So the bus bar is kind of more of like a side thing. Okay, so that's interesting. So I guess that chamfer angle actually does take a lot of space from us. We don't have to follow it one-to-one. Although that is a nice angle for the legs. That is pretty nice, look at that. But it adds a lot of space that's basically useless. Like bus bar would have to go there. That's way too tight. So let's explore some other angles here. So we said those were coincident. Let's not have them be coincident anymore. These two should be the same, so these are equal. And we should have a line here from here to here, so everything stays symmetric, and this should be a vertical line. And with those constraints in place, we can have something here. So the angle is 45. We can try 60. Oh, obviously this needs to be coincident here. I guess it wasn't obvious for everyone. Okay, well. I'm just gonna hard code it like that. All right, 60. So at 60, you know, it's not as smooth as it used to be. It's angles, and I think it's hard to tell with the naked eye that it's not the same thing. And then that's granted us more space, so now we can move the battery here to the side. And the bus bar can just be annoying here. That seems like way more comfortable. And now, instead of making it easy to remove, maybe we just have a door here on this side, and you can slide the battery in and out, and it's kind of like all you need. The bus bar cables, you set them once, forget it. It will be annoying, but it's only one time. Oh, also the bus bar, it's not modeled here, but it has all of these screw terminals here, so you can clamp down on the connectors. If we have this wall here, you can't really reach those with a tool. Something to keep in mind. Okay, so just for that reason, I think in this surface here, it's what gets removed. And we can remove from the front or from the back. Doesn't matter. I don't think it makes a difference. I definitely do feel bad because it does feel like we're adding a lot of weight to the dock here. And just as it is now, like, sure, you can pick it up with one hand, but it does feel heavy. It's not a light robot. So at some point, maybe we just need to go on and a weight loss spree. But okay, maybe we don't make these any bigger than it needs to be. So, okay, so let's go back here. We could extend these. I don't know if it adds any value extending it. It definitely makes it easier to print if we don't extend it, and we can just print like these. Printing like this wouldn't be bad though, especially if we're gonna remove this top surface. And if we extend, yeah, we can extend, right? Not by much. 6.15 on both. It's on that. Yeah, something like that. It will be a snag fit on the battery, that's fine. I think I like this. And so we would basically close these both sides and then open the top here, the bottom here. And so something like here, we would add something like that. I don't know if this is making it crazy complicated though. Definitely feels like one of those things that, oh, it's cool, but it's cool for no reason, just adds complexity. Which are my favorite things, by the way. 5. Okay, and then we round the corners. We kind of like have no way right now of adding hatches and stuff like that, other than like just like spamming screws. So these would need like 4 screws, which is not ideal here. Already have too many screws, remember? Plus, we were just saying like how the robot's kind of heavy. But just to see what it would look like, you know, it will be this. Why did that not work? My God. All right. Always something like that. And so you could service the robot from here. Seems kind of easy. I don't see any problems. Right? No problems. Okay, we do need to close the 2 ends, so let's just commit to it. I'm committed now. I'm gonna close the ends here. basically caps here. Committed to this design. We'll at least print it when we're able to, when we have more filament, and we'll see what happens. You know, add 3 merge. Why? It says we're missing a face, man. I don't know what to tell you. It does feel like we just added a bunch of very rectangular features that are not very organic. Mirror, feature mirror. I don't know why we have all these different kinds of mirrors. Feels like one mirror could mirror them all. Also, whenever you click something on Onshape, there's a little lag. Okay, reapply features. Please don't break. All right. So now we basically have a box. That's what we have. And a bus bar and a battery, right? So let me see. So battery would be like that. Yeah, like these. Okay. We'll probably fit like this, and let's just square things up here. Okay, and then actually I feel pretty good about doing a planar fit here. I think it will be planar. I guess if this is printing with this flat on the bed, we could add a draft angle to here. But there will be a lot of support to remove. So maybe just to minimize support, we don't do that. Okay, let's just start adding things here. All right, perfect. That's not what I wanted. Made it parallel with something completely random. Actually, instead of going through this trouble, let me just do this quickly. So for the bus bar, so these are 3mm holes. They're 93.85 apart, so we can just go to the torso, and same as before, we'll add them straight to our part here. This seems to work faster than like trying to commit scrap cut that something is symmetric or. Okay, so here, 74. 2.8 line to make them line up, makes sense. This line, we know it's roughly 93.850, and this was me measuring with my calipers, so I kind of like, I know it could be slightly off. Calipers are not great to measure internal diameters. Because it's a curve, right? So you can only, and the calipers are aligned, so you can kind of try to measure a point in that diameter, but calipers don't have zero thickness, so It's not the, yeah, I mean, you could get something decent, it's just not the most precise. And these walls, 1mm walls, that's what we've been doing. And then we can extrude. You know, a lot of what's wrong with Onshape, it's just like what the default behaviors are. A lot of times I just wish default behaviors was like, oh, after you made a sketch, yes, you want to extrude exactly that sketch. All right, bus bar should probably be on the other side actually, just to minimize the wire length of the wire connecting the battery to the buck converter, because that already exists, right? And I don't have a replacement. It's basically this guy, and I don't want to make it any longer because I basically don't have anything longer. I'm clicking, it's not selecting it. I'm literally clicking, guys. Like, look at this. I'm clicking. It doesn't select. Okay, now it works. Onshape works in mysterious ways. Same thing. Okay, perfect. Only took 3 clicks for a single operation. Okay, I guess we didn't properly make these. But in terms of the bus part, that's how it goes. Now there's a lot of material we can remove here. Because if you think about it, this whole entire surface I've selected here, it's not doing anything. We already have the belly of the other part on top. So all it's doing is like adding a few pins for the bus bar to exist, but that's about it. Of course, there is some truth to be said about keeping the battery safe and so on, but okay, so now we go back here. We still need to make cutouts to route cables from the bottom to the top, and I was hoping to have context to do it here. Let's see if the Onshape fixes its context. No, it still thinks the back converter is floating. That's unfortunate. Okay, so the other thing we can do is we can figure out how to make these to the top, to the pink part. Most likely something here. So most likely 4 screws. So what I'm thinking is it would be it's basically just this, right? Just close this chamfer thing we had before and put a hole in the middle. And oh, it doesn't want to. Oh, it did. All the way here. Okay, that does get in the way of the servo wires, which is probably not ideal. So maybe not that. Yeah, remove that. So it cannot be there. Ideally symmetric. Ideally as far out in the edges as possible. Can't be here. Servos can't rotate, so that's not an option. All these area here, cannot touch it because we need clearance to screw down these screws here for the servos. There is room here in the middle, but we really want to go on the outside to increase the stiffness of the joint. So that's why this was kind of like ideal. Doesn't have to be exactly there, but it would have been nice. Okay, I'm gonna go for lunch, and then I'll come back and we'll figure this out. I imagine this is already way longer than I was expecting, as usual.
Eventually.
All right, we're back. So let's see where we left off. I thought a little more about these, and I was thinking of whether we actually need a proper enclosure or not. I did mention ribs before, so we could really have just like fingers, like ribs. But I thought, maybe later on. For now, what we're trying to prove is that we can basically package everything that's required in a clean way, and this seems to be a good way of doing that. I was also looking at the actual robot closer in real life, and we had this concern with the servo wires here. Saying that if we add a rectangle here, it would get in the way of the servo wires. But in real life, it actually doesn't seem like that would be an issue. These are 26 gauge wires, so they're very flexible. So I think I'm gonna go with that way. So we're gonna have 4 supports there to connect the ribs. So let's finish that, and then let's start doing the cutouts for the wire routing here. I also figured out that I was looking at my drone, which also uses the same LiPo, and for that, the LiPo basically uses a Velcro strap and straps to the frame. So we'll just do the same thing here. We'll strap this here with a Velcro. So we just need to make a feature which the Velcro can kind of like loop around. And after that, I think we'll call this. We'll say this is done. The one other thing we could do is we could add a switch. We could add a switch, yes. I'm just not sure. I guess this is the low voltage side, this is the high voltage side. And I think I think it's okay to have the switch on the high voltage side. I'm not like 100% sure, but I think it will be fine. And so if we look at these switches, I think they give you the size of the hole that you need. I mean, kinda, right? Kinda. The mountain. Oh yeah, there's the mountain hole size. All right, so we can quickly add that. Yeah. And so I'm thinking that the switch would be. I mean, it would have to be on this wall, but there's not a lot of room here. So I wonder if the switch could be on this wall here. Right? I don't see why not. Anyways, we're working on the torso, so let's go on the torso file. First thing I'm gonna do is I'm gonna close these chamfered corners, like I just said. And so with those closed off, gonna be able to we'll surely be able to add something in order to mount the ribs. Oh, I guess actually I should have waited before mirroring. I should just make a hole first. And well, this is gonna be an M3, obviously. Basically the only thing we use here. Yeah, something like that. Right, and so we would screw from here, and and I think that'll work. Obviously this hole is oversized, like it's too long, but it's fine. It's fine for it to be too long. And let's just make sure this won't get in the way of anything else. Yeah, it seems fine. And then we could add back this chamfer here that we removed. It's not needed, but actually I won't add it back. All right, now we can mirror all this stuff. So it's a feature mirror, features here. Cool, and one more. It's Onshape is doing that thing where you click once and nothing happens. You gotta click 3 times. Okay, so it missed one hole. I wonder why. Oh, I know why. All right, there. So that should be all that's required on the purple part to mount this thing. Now on the blue part, we basically have to just add a little bit of material. We need like a flat, we need a small flat space to basically to install a why am I blanking? We need a small flat space to install a screw, and that's it. Should be straightforward. That should be fine. I mean, I'm really not expecting a lot of load here, so it's not critical or anything. You know, something like that. I know it looks not great. We definitely want to round this up. yeah, something like that. And then we can just add, and again, I don't think this will do much in real life. It's not really gonna show, but we can try to add some stuff here. It's not structural or anything, it's purely aesthetics. Something like that. Right, something like that. And then we'll just mirror these all around, and that's how these mounts. And those might be slightly longer screws. But now that we have an electric screwdriver, it really doesn't matter. We'll screw anything, doesn't matter. It takes like 2 seconds. Coming in, coming out. I used to hate it, now I love it. Reapply, and then one more mirror. It's a feature mirror. Mirror plane here. Reapply. Okay. So that's basically it. At least first pass. This will get us somewhere, or we can take a closer look after. It's really shocking to see like the first iteration here to the left randomly, and then what it looks like now. Anyways, let's see. In terms of the battery, we don't need much. We really don't need much. So can I get rid of these planes here? So if I'm measuring this correctly, so the battery is roughly 44 millimeters wide, something like this. Whoa, 44. And then its length is roughly 77 or so. So a little extra in there. And like I said, it's probably the heaviest component we have, at least in density wise. Like, I don't know, like it will probably make like 5 to 10% of the total mass of this thing. So I think it's important to make sure it's right in the middle. And as far, and as close to the center as possible. Of course, we also need room for the bus bar, but something like this. And what we need for the Velcro, really it's just something so we can loop through it. It should be very simple. It should be like, or we should be able to get something very simple. So I was thinking something like this, like a long strip. Doesn't even have to be that big, doesn't have to be that wide. Something like this. This would probably do just fine. And so I'm gonna make this, I'm gonna remove this from this part, the blue part. And well, that didn't work. Oh great, okay. Yeah, and then I need to make like a bridge across it, if that makes sense. Kind of like we'll make a little bridge. And there's probably an easier way, a more clever way to model these, by the way. But this is one way of doing it. And so basically building an overhang here. I think it's fine because we're close to the surface that's gonna be printed on the bed. Now the wall thicknesses here are 3 millimeters. So, and we want a gap, I don't know, a gap that's like, maybe like 3 millimeters is fine. So if we make this 6 millimeters tall, that's exactly how much room we need. And then we can just close this here, and this will be 3 millimeters the other way. And that's it. That will be enough to attach our Velcro battery for sure. We're gonna add some chamfers. Always nice to add some chamfers, but not needed. All right. So I think that's basically all we need for this torso thing. The last thing we need are cutouts to be able to route cables from the top to underneath. And for that, it would really help. Well, okay. First of all, let's put down the battery to get a rough sense of where things are. So if we mount it to our thing here. Okay, and so this connector, okay, that connector is there. In reality, high voltage, we said it's be here. I guess another way, we mounted everything this way, another way was mounting things this way. Would it be too let's see, would that be good? I think it will be a little tighter. Yeah, we're gonna have to stick with what we have here. Anyways, so let's see. It's the torso. Let's make some holes to route cables. So my converter is still floating for whatever reason. Onshape just decided that it must float. So I'm gonna try to guesstimate here roughly where these things should go. Let's see how big we can make them. No good sense. I guess, okay, one thing we should check is how big is an XT60 connector. So that's 15.5 times 8. So it should be able to handle at least 15.5 times 8. Ideally, add some slack there, you know, a couple of millimeters each way, something like that. And I think on the high voltage side, so the input side, the connectors are basically in the middle. So I can just use the mounting features, which are symmetric and in the middle, to position everything else. So something like that, like that. Yeah. Something like that. We're super, super close to the wall here. Or we are on the wall actually here. But wait, it's not taking off an 8. Oh. I guess it's fine to be on the wall. I guess we can we even get closer to them? Let's see what dice would look like. All right, so we're too close to the wall here. You know, it's because it's slanted. So that might be an issue. In terms of placement, yeah, we pretty much nailed that. That's good. but it won't work. Now we could make a pocket here just for that, but it does starts to feel wrong. Or we could just leave it as is and let the wires hang out of the robot a little bit. The other cutout we had here, it's a little off, but not by much. So I'm not exactly sure what I want to do about that now yet. I'm just cleaning up the other cutout here. Looks about right. Honestly, I might just leave it as is because again, it's like first pass, and I'm basically hoping that eventually we're gonna come back to it and clean it up. Maybe. I think it's very possible if it really doesn't work out. And that one might actually be in the way of the battery, which is another issue. Let's see if we can move these a little bit too. I think that might just be fine. It's kind of hard to tell, especially because we cannot model all the wires. But I do think something like that might just be fine. I wish we had more space for things here. The one thing we could try would be to try to push this buck converter a little bit this way, closer to the Arduino Uno. It looks like we have possibly, 3 millimeters there that we could gain. The only thing that Uno needs here on the bus bar are 2 jumper wires. So it's 26 gauge, very small. And so if we were to move these, let's see. By 3 millimeters closer to the Uno. So it looks like that. And I think it will be fine. This also gets a little better, just a little bit. might just be fine. It's not ideal to have such tight routings for big wires, but maybe just maybe it'll be fine. And honestly, this doesn't look bad at all. It's like a bent. I'm okay with keeping that. And then here, the wires to power the bus bar. Those make sense. Maybe power the Arduino out of this hole here. So maybe we'll make that a little bigger. It really doesn't hurt. It's like, this one's basically free. Something like that. Obviously, we do want to add fillets to all these cutouts, so that's coming. SolidWorks works as this thing where if you select one corner, you'll auto select all the others. Oh, looks like this is not a thing in Onshape. Okay, something like that. And then the other thing we need to route through our servo, like wires for the servos. The servos have 3 wires each: ground, power, and the PWM for controls. And the PWM goes to the Arduino, the other 2 go to the bus bar underneath. But because they're all in one single connector, we cannot push the connector downstairs. We actually have to bring the cable from the bus bar upstairs. So we will have a large number of wires. Now, I don't want to route all the wires through a single cutout here. It's better if we can separate the servos through the different cutouts. This just makes things more organized. So I think each servo will have its own cutout. And this doesn't have to be huge. So each servo connector, the size of the connector is it's basically 8 by 2. And so I'm just measuring with calipers. So 8 by 2, so a little hole here, 8 by 2. Of course, we do need 3 per, but you know, 8 by 6 it's not much. So let me add that right now. And that way, each servo has its own thing, and you know, if you need to access the wires for a specific servo, it's very simple to tell which one is which. I do have a hard stop in a few minutes, but we still can't print any of these anyways because there's no filament. But we did say we were going to do a leg, right? Build a mono leg next. So so we will do that. And apparently we still need to do a switch. We haven't done the switch. We need to add a switch somewhere. We'll do that after this. So okay, so All right, something like that. We do need to round up these corners, so let me try to do that fast. Of course, I'm using on shape, so it won't be fast. That doesn't feel right. That seems wrong. I see what's going on. Okay, I'll do it as features. I don't know if you guys noticed. Basically, what was going on was it has to do with like the way we built our model. We dimensioned our model. That the adding radiuses was throwing it off. So. All right, so those holes here are for the servos, very close to the servos. I think that makes sense to me. And so that's where the power for the servos will come through. All those holes honestly are probably too big. We don't need that much, but this will keep things tighter. Keep in mind there's this servo and then there's these two other servos which wires come through here and then connect through to here. So we can start there. We can start there, see how this works. Hopefully, I mean, cannot print it this weekend, but maybe like Monday next week we can have another build video. We still need to also, well, I guess build video, and also there's a lot of electrical stuff we need to fix. And if the new leg is better, we also should just upgrade to that new leg. All right, that's good. All right. So the next thing, the last thing, would be the switch of BRB. All right. All right, so last thing, adding the switch, and also I'm gonna round these corners here for this part here. Just nice to have, really. And then I guess since we cannot print it right away, that's good. Gives us some time to sleep on some of these designs. Yeah, we introduced a pretty big part today, so we might want to think more about that. I do have concerns that we're getting too heavy now. You know, maybe we need to weight the robot actually as the next thing in real life. I did make some assumptions on how heavy it would be when sizing the servos, and we might be testing those assumptions right now. All right, and for the switch, it should be a very simple rectangular hole. It says here 19.2 times 13.2. So it's, yeah, you can see it has clips there on the side. And so if the power is coming this way, high power that way, we said we could put the switch that way, which I still think it makes sense. Also looks like the battery, now that we've added that, the battery is poking outside of the okay, well we should double check that. The battery might be poking outside of the enclosure. That makes sense to me. All right, so sorry, keep forgetting. 19.2 times 13.2. So 19.2 13.2. That actually looks huge. This switch might be much bigger than I thought. Obviously, when you buy on Amazon, you can't. It's very hard to get a sense of how big things are. I think we would benefit from having these further down, just so you have more clearance to the battery and whatever might be behind this thing. This could be up to next, and just to play nice, we could round these corners, not by much, because I don't think the switch. I mean, the switch that has sharp corners, so something like that. And so that should be our switch. So switch is done. So we've completed our list here. Let's just fix the mates here. And so we could just mate according to one of the holes we've made. I'm gonna use the power hole. I think the power hole is probably the one least likely to change. And then we have one more axis to lock. Oh, and by the way, I also noticed that we didn't round those corners there for this guy. Yeah, it still seems a little odd that I still think it's a little tight, and we'll see if it works. But for now, this is what we're going with. And then I'm just gonna round every corner here. And then let's see the battery. Battery should be fine. No. We need to constrain this battery. Some more mates here. Planar mate. This phase. See, I click on it, nothing happens. Keep clicking on it, triple click, nothing happens. Okay, now it did. Okay, so I mean that's definitely 100% poking outside. So what that means is actually, is this the, yeah, that is the smallest section. Okay, so I mean, what that means is that we need to raise this by at maybe like 5 millimeters, and it might not seem like a big deal, but first of all, some things might break on our model, and also like the dog starts to look very bulky. Okay, it looks like nothing broke. Okay, we need more. The other thing is that the battery model is not perfect, because batteries are, especially LiPos don't all come the same shape, and also LiPos can literally grow as you cycle them. So it will be unwise to have a tight fit on our LiPo battery, to say the least. Unwise. Okay, so something like that. Now, as we make it taller and we keep the same angle, we actually don't add a lot of more area, right? Because at an angle, it's not as efficient. So let me make it steeper. Let's see what we're working with here. At the end of the day, that angle is literally basically purely based on aesthetics. Okay. Okay, something like that. Bus bar has a lot. It seems like it has a lot of room, but remember the 28 wires coming out of it. You know. This is actually the switch now, so it's not the interference hole. So this is a switch, and looks like something broke here. Yeah. So before we were constraining it to that odd slot that was popping out, but now that doesn't exist anymore. So okay. All right, so the switch there, I mean, we didn't model the switch. It's obvious that it's gonna interfere with the battery there, right? So can't have it there. And in terms of aesthetics, it does seem a little odd. I want to see how this looks in real life though, before we make any decisions. Like this seems like the package is like going really down, right? But if you imagine the blue part and the orange and the purple part as one, and just bring it up, everything up a little bit, so center it with respect to the legs, I think we'll be fine. So we might have to do something closer to that. There's also a world where we figure out how to package things up here on top of the servos and stuff. If we would rather be taller and have a fat belly. There's also the fact that we don't have to use a 6S LiPo. The battery is it's pretty big. We could also just move the battery to the top somewhere, because it's taking a lot of room here. And it does look, I do think it looks a little bit silly. Trying to picture what it's gonna look like. Alright, so I'm gonna move this switch up here to the front, and then I think we can say it's over, or it's done for now. Then maybe we'll come back to review later. I do think this is probably not the optimal design, just based on how much room we're taking. I mean, I did get the wrong side, but other than that, I think it looks fine. The switch would be there, on and off switch here. Yeah, I don't think I hate it. I hate it. No, it's fine. The top obviously looks better. Like the more mature design obviously looks better. It looks like we've thought about it more. This new thing, I don't know about it. Oh, also we broke these things. Need to fix. Not those. These scissors are broken. Because we changed the angle. These things are. They're gonna need to grow taller, basically. Kind of like that. Again, this all hurts the aesthetics, but okay, and that might be too tall for a screw, right? If you think about it, these things do need to. Like, I don't know if we have screws that big. So we can change this to a countersink. Sorry, to a counter bore. Not a lot of room for a counter bore. Or we could make this flat here. Either way, the aesthetics are getting hurt. When I laid all these features that were the mirrors and stuff like that. Oh, no. Not the sketch. Okay, so we're gonna work with this sketch here. And basically, oh, okay, basically we're gonna take that sketch and we're extruding before. Instead, we're gonna remove. Okay, you can see removing was not enough. I mean, I'm not sure why it's not working. Something like that. Except we also need to. We need more room. So we gotta change the sketch here. I mean, sketch had the right idea. It's just we need more room. Part of my sketch here is going to be flying. It actually doesn't matter because there's nothing to cut anyways. So something like this, I think. even more room. So it's weird because it doesn't want to cut everything. It's not following the sketch really. And I'm not sure why. Oh, I guess it's going through the wall. These are on-shape issues that I'm having fun trying to solve. Okay, just delete everything here. I can visualize in my head what needs to happen. I just need to convince on-shape that it's indeed what's gonna have to happen. And so, okay, let me try a different approach here. So instead of removing material from the start, let's try adding material and then remove. So I think construction, okay. I don't know why that would be fully constrained. Oh, I guess the thing is, okay, and I know it's hard to see just because the sketch lines are blue and the part is also blue. I do gotta go soon, but let's try to finish this. Man, I have so many bad things to say about Onshape. Okay, so it only wants to, it's interesting. It only wants to extrude parts that are not interfering with the initial part for some reason. I cannot understand why. See, half my sketch is not coming up. I don't need it to go. This is gonna be a very awkward way of doing this, but gonna make it work. think maybe this will work. Maybe. I mean, ideally, we get even more space for the screw head, but we are getting closer to it. Let's see. Okay, I remember now what I wanted to do. So it's not entirely that. It's kind of more like this. Basically this. And so we kind of like create a pocket here. We create this pocket here where and I do realize that was way too complicated. I don't know, would that be fine? Can we even access this screw? Yeah, we can. I think that might be fine. It's not ideal, not a lot of material, but the alternative would be to move this guy a little bit, which we probably also can. It's starting to get very tight now. I don't like how this looks, especially from the top. I think I'm gonna go with this here. Yeah, something like that. I think it's very complex, and it's barely hanging in there, but yeah, we've complicated this a lot today. But for good reason, because right now what we have is a mess. So cool. All right, that's basically it. No interference anywhere. Much tighter packaging of the electronics, wire routing. Everything looks good. We've crossed everything in our list here. The next thing is building the monolith. I'm gonna do that tonight, so I'm gonna go away for a little bit. I'll come back and we'll do that
later.
My friend Kenneth actually just shouted out the channel on Twitter. He has a big following, almost 30K people, so pressure's on now. We gotta perform. But anyways, yeah, just to recap, this is where we're at now. This is what we built today. We've packaged everything very neatly here. We have our Arduino, our buck converter. We have routing for the cables. Everything's very neat. We ended up adding this belly for the dog. I still don't know how I feel about this. I don't like it. I think it makes it look heavier. You know, kind of throws off the proportions, but for now it'll do. I'm just trying to prove that we can really package everything in one tight package. And then the other thing is, like, we would likely move away from, you know, from this bus bar, from this buck converter, onto just a single power PCB. So I've never built a real power PCB, like something like that, that's not gonna burn down. So I'm gonna ask for help to an electrical engineer friend, and maybe we'll have a stream together with him tomorrow or the day after tomorrow, and maybe he can help us. But for now, I think this is looking good. There's still a lot of sus things happening here. For example, these, it's not great, but it's much better than what we have right now. Just as a reminder, this is where we're coming from, right? Spaghetti wires. Now, I wanted to do two last things before we move on and build our monoleg. The monoleg is the leg with no screws on. So first of all, we added this thing for the Arduino. Oh, I'm lagging. We added, Ownership is lagging here. Hold on, let me close some apps on my computer. Yeah, so we added mounts for the Arduino, and we made it flash from the outside. Why am I lagging so much? Let me refresh. Where I was going into is, like, the Arduino USB port is now flash to the outside, but we haven't made a cutout for the USB port, so we cannot actually connect to it. So let me show you. So here, you see here, there's no cutout, so we need to add a cutout for that. So let's just do that right now. I'll take 2 seconds. I don't know what's wrong. It's kind of lagging. Yeah, so we just go here, and basically we can use these and these. Yeah, kind of like that. Yeah, that'll do. I'm just gonna make a new rectangle here, and I'm going to maybe add some clearance. A millimeter clearance for something like this is a lot, but yeah, maybe we can go with like 0.5 millimeter. We don't need these things anymore. Okay, just delete everything. Start fresh. Yeah, because you can see the outline of the part here, so I'm just gonna go with that. Here, here, just like that. And so now we can just remove this section, and we'll have our Arduino port, kind of stuff like that. Feels a little tight, no? It does feel a little tight. All right, something like that. And of course we round the corners because we're professionals here. All right, cool. So that's it. That's that. And I guess the other thing I wanted to do was these holes here that actually look very bad because, you know, they're basically almost outside of the like that very thin wall. We might as well just make that a slot. We might as well just finish it. And so I think that we can roll back these. We can roll back the mirrors to when we just had these, and we can basically create a rectangle here to finish it off. Now normally on SolidWorks you can just kind of use the center of a circle as a midpoint, but I guess here we have to like create a circle, a point. That's fine. All right, remove. Okay, and now we need to add this to the mirror, this new feature, because we're mirroring features, so we gotta add that there and add that here. And so now, you know, it's fine because, you know, obviously slots don't constrain it on all directions, but the bilateral direction is constrained just by the fact that there's 4 holes, right? So it can't really go anywhere. So that's gonna be fine, and it looks cleaner. It's definitely cleaner. Yeah, so that'll work better. And I think that's it for now. Now, we're not gonna print this on this video just because we're literally out of enough like filament. We basically have to print the entire robot, and since we're printing so many other parts, I want to print new shoulder joints based on the improved geometry that we talked about earlier here. This one, moving away from this one to this one. The difference is just, you know, less support, kind of like more concealed. So I don't want to see servo motors from the outside. And then the other thing would be markings on the outside, so you can see which side the part goes on, just with markings. And a better fit to the servo, so it doesn't slip when the servo kind of like trips or something like that. So look at all this play here, and this one's like very rigid, very strong. So that's what we want. But I think for now we're basically done. So we're gonna wait for the new filament to get delivered. We'll print everything, and we'll also fix the electrical, and then we'll have the hardware on basically at a point where we can start to work on the software section again, and we can learn to walk, which is, I think that's where we're going to spend the bulk of the time, really. We just want to have a really robust hardware platform, so we don't have to worry about we don't have to worry about things breaking. Let me close this up. All right, so that's it for now. The next thing is this thing called the monolith, right? So we wanted to build a monolith, and by monolith we meant, I'm gonna mark this done. By mono leg, we meant a leg that has no screws basically. So right now, you know, when you print the leg, we have to put heated inserts for this part here. We used to have a heated insert here and a screw here. We have it down to just a snap fit, but it's still two parts that you cannot put together. We have a screw here with a heated insert here. We have two heated inserts here, a screw and a screw and a screw. Then we have a bunch of screws here. The servo horn screws, those are gonna stay, like this one and this one, but every other screw should disappear. So we're gonna try and experiment. We're gonna see if we can make that happen. So yeah, let's get started on that. So first of all, you know, gotta make a copy of these, I guess, somehow. This is where we learned how to use where is the part? Oh, I guess it lives in here. We're learning how to use Onshape. Move document, no. Export, duplicate. Yeah, duplicate, but I want it to be outside of here. Don't just duplicate it here. And if we export these, press solid, can't really export it. Well, one thing we could do is we can export it as a step and then bring it back as separate parts. So, I mean, let me try that. We're gonna start with the right leg. We're gonna try to replace this green leg. So since we're replacing, one of the conditions is gonna be that the geometry needs to stay the same. So same leg width, all the linkages need to be the same, just so we can hot swap it. So let me start a brand new assembly here. I don't want any of these parts to overlap, just in case this ends up going terribly, and we don't want to use any of these. Import files. Right, so when you're importing a step file, you can import to a single document, split into multiple documents, combine into a single part studio. I think we can combine it to a single part studio. Let's see what happens. A part studio, if you're coming from SolidWorks, and it's important right now here, it takes a while. A part studio, the way I understand it's basically just a part, and then you have assemblies, and that's what assemblies in SolidWorks. Except here on Onshape, an assembly can hold part studios, and so that's where the part actually lives. It's not like a separate part file. It's kind of like, it's a little bit different. But anyways, we have our step file here. It's in a part studio, and you can see no features here, nothing on our feature tree. It's just the import. But then you can see 26 parts here. So we can remove some of these parts. We don't need them, right? So, well, okay, not all of them. So if you click any part, you'll just highlight it here, and you can, there's gotta be a part, remove, delete part. You can delete parts. You can just select which part you don't want. So I'm gonna remove all the stuff that we said we are not gonna modify. You know what, actually, there's something missing here. Let me delete these. Let's try that again. So I noticed that we have the old servo horns, and we need to go back and update to the new servo horns. So this is the right leg assembly that we currently have on our top assembly. And then if we import or we insert new parts, we have a file called servo horns somewhere. Or we should, yeah, consolidated servo horns, and then the knee horn is here. This is the actual knee horn that we want. And so we want to replace this guy here. And I'm just gonna quickly make this guy in place. This is probably not a perfect mate here, but okay, so we can remove this nut also. We never actually used that nut. We're gonna remove this fastener here, and you know, at some point we might come back and clean the fasteners. If tonight's goal is correct, we will not need fasteners at all. So now that we have the right horn, we can actually export these and do the whole import again. So I'm gonna call these B2, export, and then we go back to our new folder, monoleg, and then we import it. And maybe I jumped the gun here because I don't see it. I guess sometimes the exports take longer. I mean, it is loading. Yeah, it's being prepared. You will receive a notification. So I guess you just wait for this to happen. While that waits, I'm gonna remove this servo disk also. This is all geometry. We don't use that anymore. I don't know what's taking so long. Export completed. I think it's working. I still don't see it, so I don't know. I don't know if I'm missing something obvious here. 23, no, that's not it. Mono leg start. Okay, it's loading. You'll receive a notification. I think this is the notification step. 727. Exported successfully. I don't know why it's not actually exporting. Maybe it doesn't like that you change when I change the names. There should be a pop-up that asks you where to save it to. Gonna just refresh. Just some classic unshaped bugs. It says exported successfully, but to where? It never asked me. And it says download. I'm not sure what's going on here. I don't know where it's exporting them to. It's not here. It's not here either. Alright, let's try that one more time. I just need to update the geometry. I don't think that will change anything, but Exported successfully. To where? No clue. Store file in a new tab. Let's try that. Oh, that worked. It's here. That's not what we want. But maybe from here we can download it. Just adding some extra steps. I guess maybe my browser is blocking Onshape windows somehow. Is it because I'm recording screen? I don't think so. Just OnCat being weird here. Yeah, nothing happened. Let's see if they're having issues. Apparently not. That's annoying. I'm gonna restart my browser and I'll BRB. Now it works. Basically, the trick here is to restart your browser when Onshape is acting up. And so now we can keep going. Combine everything to a single part studio. It's importing. It says it was successful. I don't see it, so I'm gonna refresh, and there it is. So it's a little clunky. I mean, browser based, I guess. All right, so it's the same thing as before. I'm gonna delete some parts. So I'm gonna delete the parts that we know that we don't want. Things we don't care for, fasteners, you know. That nut there, we don't care about that. Don't care. Don't want. No. Basically, just getting rid of all the fasteners. Don't need these. Can't really see what's in there, but okay. And as usual with working with legs, I'm gonna start from top to bottom. Now, like I said, we already have this geometry working pretty well. Let's see if I can do a section. I can do. Yeah, this is already working pretty well, this fit here. Let's actually remove this part also. Delete part. This part, don't need it. So this fit, it's already works. It's what we use on all legs by default, and it works pretty well. If anything, we can tighten it more, but yeah, we could tighten it even more. As a baseline, it works pretty well. I think the clearance was 0.25, you know, 0.25, and it was like a 10 outer diameter to a 10.4 outer diameter, so kind of like 0.2 all around, and then 0.25 axially. It seems to work fine. What we could do is basically there's no need for this to be hollow anymore, so we could you know, just in the interest of simplifying geometry, we could just kind of like remove these faces here and have it be solid like that. So that's basically what's happening here. And then I'm gonna move this face a very small 0.05. It'll probably make no difference. I think my nozzle is a 0.1 millimeter nozzle, I think. Let's see, bamboo P1S nozzle. It's a 0.2 millimeter nozzle, so removing 0.05 will probably make no difference. But let's try it. So that joint is pretty good. Now, what we did on that joint, we want to do everywhere else. And maybe we also want to think if this is good to print, because we'll probably print something like that. Or like, I don't know if it will make sense to, no, it'll probably make sense to print flat like this. But we're gonna have to have a lot of support. And the whole point of having this giant opening here, which will require support because it's an overhang, was so the part could flex open and could slide it, the orange part could flex and slide onto the gray part. But if we're printing this as one part, we do not need such a big opening anymore. Let me see what's happening here. So this is back when we were actually adding threaded inserts onto our model. We don't need that. We are not gonna need this hole. We don't need this, that, or this. So just solid. That didn't work. That was too ambitious, maybe. Let's try that. I think, yeah, I missed one face here. All right. So obviously it's very simple to incorporate these onto the leg here. Like we could just literally merge the two bodies, but I was thinking this could be an opportunity to try something else, because the one thing I did notice with these rounded feet is that there's basically no traction. And unless you're perfectly, like you place it like perfectly on the very small flat surface here, you're always like basically standing on a little point. And my forks are like vinyl, and so the robot is basically just like ice skating. Okay, where's everything else? A lot of parts disappeared. Okay. Yeah. All right, we'll start here. It's an easy place to start. So let me see if we have a plane. We have no plane that's favorable here. Let me start a plane that's like through the middle of, and I think there's no mid plane on shape, is there? It is, there is. Okay, so we have this plane here. I'm gonna rename this plane to, let's see, rename, lower leg, or yeah, leg mid plane. It's not for the entire leg, but it's for the two leg components. Obviously, once you're up here on the cams, that doesn't work. And so on this leg here, I'm gonna draw something out, and this isn't exactly flat, to be honest. So let's see, what's our top plane? So from here, let's hide the standard feet for now. Top plane to here, there's 0.2 to 0.5 angle. Rotating this whole thing is going to be a little annoying. So okay, so maybe we'll just work with what we have right now. But I was thinking that we could have a feet that, obviously we're going to build on top of what we have, because it's not a terrible design. It's kind of works. So a foot like this, and make this perpendicular. We cannot use our vertical and horizontal parameters because the leg is not horizontally, it's kind of like in a weird random position. We could have fixed that, but let's keep moving here. And so I want to have something like this, and it's gonna be like not the complete circle, but maybe something like this, and then we're gonna cut this, and yeah, like maybe like 30 degrees both ways, and maybe we can borrow this surface here, right? And so use this to basically cut. So I'm gonna make this coincident. It might be hard to tell, there's a sketch line there because of the colors, but there is. So Gonna cut these like that. Gonna set a radius of 35, just to constrain things here. So I was thinking something along these lines. This point is kind of arbitrary here, just came because I imported this intersection. But something along these lines, along the lines of these. And so if we have these, then now that we have this sketch, I was going to delete this part because we don't need this part anymore. And I was going to maybe delete some faces here. I don't know what happens if I delete these faces. Yeah, something like that. Yeah, okay, yeah, that's neat. And now, actually we can go back to our sketch. We don't need to go back to our sketch, but we can use this geometry, and there's no midplane. Oh, okay. Up to face and grow it up to here, and then the same thing on the other side here. Something like that. I don't know why it's transparent actually. Oh, okay, it's not transparent anymore. Something like that. It does look a little off now. Just because this angle needs to go. Whoa. Alright, we'll just, yeah, okay. Well, maybe we can do some, oh, sorry. Maybe we can do some magic here and just delete face our way to success. When in doubt, just delete. Yeah, that worked. Okay. And of course, some fillets here and there. And oh, too much. Something like that. It's a little more organic, I think. And we do want to incorporate the same chamfers as we had before. So here, I don't know if that's not gonna work, is it? No. Let me see if I can match this chamfer here. Else we can remove the chamfer all the way up and make a new one. That'd be a little painful. Well, let's measure it. Seems a bit arbitrary. Yeah, something like that. Oh, forgot to do the other side too. So something like that could be our new leg, our new feet. We'll probably round it here. No. Okay. Okay, so that, like I said, I don't think we need this big opening here anymore. Although this big opening also acts like a stop for the leg. It's an unintended stop, but it adds like a stop here. This is actually where the leg stops. If it wasn't here, it would be up here. Actually, almost matches the same thing. That was a happy coincidence, actually. I did not intend for that to happen. Yeah, so if it wouldn't happen there, it would happen way earlier. Yeah, I mean, maybe we can keep that as is because it's working pretty well. Okay, so next up, let's see here. So, I mean, the most basic thing we could do here is we could just delete this face and add a cylinder through here, right? That's the most basic thing we can do here. And there's no clearance here. So maybe we can move this. I don't know if there's a move part. We want to move the entire part. Is there a move part? Move. How would you say move? What's the other way of saying move? Translate? Transform? We want to transform these in the x-axis, looks like, by 0.2. Other way, other 0.2. Minus 0.2. Alright, so something like that. Again, 0.2. I mean, we do have a, what did we say? We had a 0.2 nozzle. So 0.2 seems okay. And then we can add a cylinder here. So this is one way of getting rid of. Oh, why does it look funny like that? It's probably because we had a chamfer on that edge. Okay, so we could here. We could make this concentric, of course. And I think we can, yeah. Oh, okay, it's not concentric, I guess. Yeah, something like this here. And well, here we do have to actually measure. Can't go by vibes here. But oh man, so many planes, so many planes. Gonna hide some planes for now. All right. So this is at least 3.2. We said 1 of clearance, so 3.3, and then we need to add a cap to lock it axially. But in essence, that's how it would work. Of course, this doesn't necessarily give like, oh, very structural vibes at all. But let's try it. I'm willing to try it. Same with these, right? If you think of printing these, there's gonna be support for all of these on top of this part, and that's gonna be very annoying to print. And so we might want to do something about that. But let's keep going here. A cap of 2 millimeters. And then another 2. Yeah, something like that. Do you think that, guys, that will work? I mean, it will print. That I know. Is it gonna be strong? That I do not know. Also, we probably don't need these chamfers anymore, right? The only reason I would have chamfers there is to try to fit a nice fillet here. But it's gonna be very small. It probably won't even register. You know, something like that. But then we don't really need fillets here. We probably need another, no chamfer, sorry. We probably need another fillet here. So we could do something like this. And whatever we're doing here, we're just gonna copy across because a lot of these joints are the same really. So we could do something like that, right? And so you could see how, you know, that's basically a joint, just assuming it doesn't break. Like I said, we're gonna print like this, right? This is our bed here. And so the layers are gonna be stacked across here. And so if there's any load being transferred, those layers are gonna be loaded in shear, which is not ideal. We would much rather load the filament in tension, but we would have to print it in a separate way. This is almost like a single shear scenario. It's really not ideal. Okay. I'm just curious to see how would the slicer interpret these. So let's actually take this to Bamboo and see what it thinks. Let's see if the exporting function is working this time. Oh, yeah, let's see. I just want to see where it's adding this, where it wants to add the support. Okay. Well, okay. Another thing to notice here is that we'll probably have to position the leg strategically so it actually fits on the bed, which is not a big deal, but currently it doesn't. It's gonna throw me an error. It's gonna say it doesn't fit when it can totally fit if it was in the right position. Yeah, it's this pin here in question. So let's see if we can at least like slide it. Oh, we can. Let's see. Okay. So first we need to make it fit. Okay, so for that we need to do a transformation. Entities here. Translate by rotate on these axes. And 30 degrees other way. Probably more than 30. Probably 90 degrees here. Of course, if we translate this by 90, we got to figure out how much everything else has to translate, which is makes my life harder, you know. Let's see if this works. Mate connector. Oh yeah, that works. Huh. And then these can transform, rotate, axis, these axes. It's not the exact, it's not, just because we rotated the other 30 degrees, it doesn't mean, like, that's not how it works. These will have to also translate. Let's see if I can make this work. Transform by mate connectors. From mate connector. Looks like that worked. Just one more translation. Transform. This is right, so that kind of works, I think. I mean, we still need to fix this horn here. This guy can float. That's fine. Oh, this is off. This might be a little harder than I thought. Because if we move it here, yeah, it's a whole thing. I should have done this before exporting it. The way I would approach these right now, it's probably a little bit of guesstimation. And of course, if you get it wrong, it's not good. It's off by a lot. It's off by less now. it's all off by very small now. It's very, very small. It's getting smaller. I think it's getting smaller. 48. This is not linear, of course. I think for the sake of our experiment, this is pretty good. All right, let me try exporting that again. Just download it this time. STL. Yep, it fits. Oh, okay, it's crooked. Weird things are happening. Okay, a lot of these parts are not needed. We have a servo horn in there that it's actually not needed, so. I don't know why this feature of like lay on flat on bed is picking such weird surfaces. I guess we can do this one. Oh, I guess it's the other side that we want. This. There are some weird angles in this, like. Alright, let's slice it. This almost looks like we found a dinosaur. Really, we only care about the pins though. And we gotta make sure support is on here. Just to see how it would slice it. Alright, so a lot of support out here, support here, on this pin here. Whoa. The way bamboo handles rotation is different than on shape, of course. Alright, so we can go layer by layer. Basically anything that's green here is support. Oh, sorry, that's not it. Okay, so we can go layer by layer here. This looks fine. And this is where we start with the pin. So you can see here, inner wall. So basically the orange line here, one of them is the outside of our pin and the other one is the outside of the inside diameter. And it kind of like, it seems to be like a very, very small gap. There's no support or anything between the gap. It's that small. I do see internal solid fill. So this purple here in the middle of our pin, that should not be happening, I think. But it's not for the entire duration. It's just some of it. And that just could be because I screwed up the rotation. I don't see any support for the so our clearance is so small there appears to be no support, so that's fine. Let's look here. So this is the other joint, the bigger joint, the knee joint. Again, no support. Clearances are so small. I do wonder how that's gonna print. I mean, on the slicing, it does look like what I wanted it to look like, so that's good. I'm curious to see how it's gonna print. which is the entire point of this experiment. Can we have mates on a port mate connector? I added a mate connector. I don't know if that's gonna do anything. Let me see if I can, if that actually helps. What happens if we add another mate connector? I actually don't know what mate connector even means. Yeah, I don't think that's it. There's another option that we could do. Basically, this rod here, it's so basic that we could just recreate it as long as we keep the yeah, just to be safe, because I can't, I'm losing a lot of time just trying to rotate things here. Obviously it's painful, but yeah, we can just recreate. This is basically a rectangle, right, with 2 holes. It's not hard. So 3.2, the distance between the axes is 130.2, right? So we can basically delete this part and just recreate it, something that's perfect. And while we're doing that, let's turn this into a pin also. And so I think this pin is sorry, that's like connector pin 3 mm diameter. Wait, are these on the same plane? Oh, they're not. Should they be on the same plane? So maybe we wait a little till a little later. To make sure everything's in the same plane. And then the other one is 37.6 centimeter for cam 2knee. Okay. So if we think we have those pins figured out, I think the next thing could be to wait. What's the distance between these and these? I see the issue. That distance is also off. Okay, I have an idea. What I'm gonna do is I'm gonna export this leg, which is basically the only thing we've changed so far, as a step. I'm gonna go back to the other assembly. I'm gonna add it. This is gonna sound very complicated, I think. I'm gonna add it to the other assembly, and then I'm gonna export it again, and that way all the kinematics will be correct. This is like the extra steps way of doing this, but extra steps way that works, which is what matters here. So we don't need these. Okay, and then we can insert I think there's a way to insert from your computer. Maybe not. I'm just gonna import it here. It's importing. I wish there was a status bar or something. It's just text. If you miss it, you might be waiting for a while. So insert. I think this would be it. Yeah. Oh. Okay. And so now, just with a couple mates, we can have these properly placed. Cylindrical. Remove this part. Remove this part. Come on shape. Remove this part. Another cylindrical. This is kind of how we should print it, I think. We can do a planar here, here, with an offset like that. Okay, and I think that's fully constrains things. Oh no. It doesn't. Okay, well, there's no mid plane for the, I guess we know that from here to the inside. I'm clicking and it's not selecting. Okay. It's 0.2, right? So just to minimize print space, something like that. So now if we were to export this again, now that should work. Geometry should be perfect. So yeah, so apologies for the extra steps, but you know, we do want to get it perfectly correct. So here we go again. It's like the third try, I think. Monolith. So I'm gonna rename that to archive or something. JK, I can't rename. I'll rename archive. For the most part, Onshape has all of the features that you would expect. Things like basic things like, oh, this is where I would rename something, stuff like that. So that's good. It's importing. Still importing. It says it's completed. I don't see it. You gotta refresh your page. All right, you see these? We see the triangles and stuff like that, the trapezoids. That's because we export it as an STL instead of a step file. So we need to go back and export as a step file. STL is good for when you're 3D printing. Step file is what you want when you're exporting 3D geometry across, across different programs. So same thing here. It's preparing to export, exporting, it's saved, and now we go back and we try again. All right. So a few things. We did lose some things. For example, we lost being able to modify these because that's on the old file, right? So all the features to modify that. Also, we need to fill in this hole again. Of course, that takes 2 seconds, but okay. Oh. Okay. And then we need to transform these by, pretty sure it's 0.2. It looks like I did it wrong on the other one. Minus 0.2, I guess. Okay. So that looks fine. So now we can go back to deleting this face and replicating the pin that we have on the other side, but on this end. Yeah, so let's do that. Okay, so one thing I noticed is that this face here, this pin is, it's like this face is lower. It's not aligned. So this face and this face are not in the same plane for some reason. I don't think there's any particular reason, any good reason for that. At least not that I can see right now. Maybe something in here. Let's take a look. So this, of course, is kind of like a mess, but as spooky as it looks, it's actually not that bad. And I don't think there's any particular reasons there for that to not be in the same plane. Let's remove some extra parts here. We don't need these. All right, so what I'm gonna do is I'm gonna move this face so it matches, so it's on the same plane. So move face, and that's 1.294. So what happened? It doesn't want to move the face. One. It doesn't want to do it. I don't know why. Oh, because I guess it'll break some kind of jump. What jump? I think it's because, and this is a bit confusing because it doesn't tell you, but I'm just guessing that it's because it's gonna break some chamfers. I personally don't care about the chamfers whatsoever, so I'll break them first, so it's not scared of breaking them. this should work now. Yep. I knew it. All right. So here and here. Okay, perfect. And now we can actually recreate the pin. Sorry, what's broken here? Okay. This is the pin sketch for the pin. We can move this here. I think it's like a 3.3 or 3.2. This is the first time I tried to do anything like this, and it's really because like thing like Bamboo has made me very confident that, you know, I can actually print things like this and it's not gonna fail. 3.3. Oh no, sorry, I just read that 7. 7, and just try to match the exact same pin as before. .5 maybe? I don't remember really. So it's like definitely 7 and 1.6. Why would it be 1.6? That's kind of odd. Okay, 1.6. Oh, the clearance, I went with 0.2 there. Clearance, interesting. And I only have 0.1 here. Well, for consistency, I'll match it. So 3.3. And then I have some fillets there. So obviously, it's gonna be like a 1 millimeter because can't really fit anything else. And then we can remove, sorry, we can delete face, delete these. I should be memorizing the shortcuts already. Probably saving some time here. But something like that. Yeah, it's basically matches the other pin. So our two pins are identical. And then we gotta replicate the same thing twice here for this one. So you guys get the idea? It's pretty basic stuff. Now the offset here is bigger, and sorry, this is the lead part. The offset here between these two parts is way bigger than the other ones, and I think there's a reason for that. Like, I think that's true in real life for sure, and I kind of just been ignoring it. But all my connecting rods here are a little crooked just because of that offset. That offset is real. So instead of ignoring it, we could, you know, there used to be like a nut there to make up for this offset. We could just grow one of these parts to fill in that gap. The one thing I don't know is if this gap is representative of what the gap is in real life. And we kind of need to know. So I guess we're gonna assume that it is representative. It really depends on, you know, where these things sit on the servos and so on. So harder to measure, but also we have 0 clearance here. So we need to transform these. Like if you don't have any clearance between your parts, you're basically gonna fuse them when you 3D print them, right? Because it's gonna print as one part, and you don't want that. So yeah. I'm gonna copy the exact same geometry on all pins. Another approach would be to do something slightly different on all the pins and then decide, oh, what works and what doesn't. I think what we have is gonna work. So I don't feel like we need to try a lot of different things. And if something doesn't work, it's because it's gonna fail in shear. And probably not because the tolerances are loose or anything like that. This looks more like a toy. I don't know. I really wouldn't. I don't know if I will trust it. Our servos are kind of beefy. They can put out a lot of torque. These guys might be in for a bad time. Okay, let's see what's the, this is some blind trust moment here. We're at 2.46. We're gonna bring this up. We're gonna bring this up by 2.3. Our gap is gonna be 0.1 basically, so ideal. Should have just put the pin, and now we're gonna put a pin here, same as everywhere else. And let's see what happens. I guess the other challenge is actually printing these. Putting a lot of trust in the on the bamboo, but maybe just the print also could fail. So a lot of overhangs, a lot of plastic. We might also run out of filament mid-print. That could happen. .5. No, not a face, man. Not a face. Whole sketch. Yeah. All right, so it's that pin. So those are all the pins, all the joints, except for now the fun part, it's in here. So let's take a look again in here. It always looks way more complicated than it really is. It really helped a lot to assemble this in person. And okay, so right off the bat, some parts we can eliminate. We do not need the bolts represented here. Now, I only left here these here for reference. These two ports are now one. We actually fused those two ports a few videos ago. And I just left that for reference so we know how things interact. And really what's happening here is this like retaining ring needs to be incorporated into this part. And that's it. Everything else can stay the same. And yeah, I guess we need to make sure there's some clearances in between everything so it doesn't fuse when it prints, but other than that we can just delete this part, and yeah, there's interference on this retaining ring. Obviously do not want that. Yeah, so I'm gonna actually delete this retaining ring. You know, I think it's pretty obvious what needs to happen here. Delete face. I don't think we need this overhang here, not like it is there anyways. I think red means it's not happy or something. Okay, yeah. yeah, something like that. And oh, actually, bring back some parts. Yeah, I guess the one thing to keep in mind is that that horn, that's going there, so we do need to clear it. But basically what we want is this. We want, well, yeah, we want a circle that goes all the way here and has some clearance here. And when it goes all the way here, these should be equal. And the clearance here should be here, and you know, should be like maybe like 0.2 or something. It's a major joint. And then we fill that sketch the other way, all the way to up to face here with an offset of like maybe again 0.2 or something like that, 0.1 since it's axial. Yeah. See, I think that's basically, that will do. Yeah, that will do. And so now we can exit this view, and this would be it. This would be our one part leg, our mono leg. Let's rename it mono leg. Yeah. So back to the slicer, but I think this is done basically. And so the last bit is, you know, making sure we're picking smart faces to place on our bed. This might be an issue. This, we kind of like don't want that to be our main face. Alternatives. No good alternatives. I guess that can be our main face. That's just gonna lead to a lot of support, but we definitely cannot get rid of that. I didn't realize that was the lower point. Let's take it to the slicer and see how it's looking. I name all my files the same thing. Copy one. Okay, so prepare, remove these, add new file, copy one, bracket one, classic, and I guess that's what I'm understanding. Okay. Yeah, see, like there's gonna be a lot of support. Support normal, okay. And slice it. I think if it's anywhere under 4 hours would be great. So print time 2 hours, that's nothing. A lot of supports, all that green stuff is support, a lot of support. And we can triple check the joints. So for example, yeah, this is the knee joint here, I think. No. Yes, knee joint here. It's okay if there's support in between. It's just we don't want to see support in between the pins, because our gaps are small enough that it should just work. Also interesting to see, look in here, see how it looks. Oh, I guess the other thing is we could have incorporated the servo horn into this part as well. Because right now there's four screws there. And I actually deleted the servo horn earlier. Right, so technically we don't need these 4 screws. Let me bring back those horns. Yes. Okay. All right, so technically, so don't need the servo horns. Oh, actually, do we? Let's see. join parts, merge, connect, join, make joint. That's not the same thing. So these and these. Boolean, union. Now it's one part. Now we can delete face. I understand there's a lot of blue here. Let me change this to magenta or something so it's very clear what's going on here. Okay, so in theory, let's go section B here. Yeah, so we want to merge the magenta part with the purple part with the gray part here. So it's like 24.85 diameter, 24.85, 4.15 difference. Move, oh, sorry, move face. See, I would have totally been like, oh, we'll remove the screws in the next video, but since people are watching, I'm like, no, we gotta do it now. Can't be lazy. Okay, so now, at least in theory, we can Boolean join this part and this part, servo disk union, and we can eliminate some of these faces that we don't need. This also has some implications in terms of how much support is actually needed. We'll cross that bridge in a little bit. I don't know why it's not happy. Oh, should be perfectly happy. Okay, it's happy. Okay, see, it looks much cleaner. Feels a little bit iffy because, but let's see that cross section. I don't know if I'm missing something really bad here. Obviously, this doesn't make sense. How this doesn't make, no, that's not what I meant. Yes, that's what. Yeah, something like that. Yeah. Now the one question is, what is keeping this part from falling axially, right? Because before, the servo horns used to kind of like come all the way here. Now it doesn't. So this part is not constrained in any way. So we need to constrain it basically. And that's easy. Constraining is easy. We're basically, it's funny because we just eliminated the retaining ring. But in a way we're bringing it back because the horn was also acting like a kind of sort of a retaining ring. So I'll just do this quickly, but basically add here, that, and then another circle here, with some clearance here. I can add big clearance. And then, I don't know, this can be like, this doesn't have to be huge or anything. What we do need is a starting offset of like, I don't know, maybe like 0.1 since it's axial. And it will look something like that. We could probably clean this up a little bit. But let's see that cross section. right? So now the blue part can't go anywhere. It will just be printed in place. So yeah, I think we can. No, I think that's fine. Yeah, we can print this as is now. All right, back to the slicer now. I don't see any issues. Yeah, back to the slicer, exporting for the last time. I'm gonna go turn on the 3D printer. All right, here we go. Very curious to see how this turns out. I'll update as soon as this is done. Although 2 hours, it's probably gonna be past my bedtime, so probably tomorrow morning, but maybe we don't use screws anymore, ever again.
Tomorrow for sure.
Good morning, it is now the next day. Print should be done. This is what we printed. These are our pliers for the support. And let's go take a look here. Yeah, so it looks a little scary, right? It's just because there's a lot of support. It's like, I don't know, and look at those pins. They look very, looks like it's fused or something. You can't really see any clearance. So let's take it out and see if it works. This is the thing. I'll try to stay in frame. I noticed yesterday when I was showing the robot, I didn't stay in frame. It's kind of hard to tell where the frame ends and where it begins. But anyways, these are like a lot of support. We knew that would happen. Other than that, it does look like the real thing. The new food here looks very smooth. I like it. So I'm just gonna pop it. And it's funny because like this printed all night and the printer is pretty loud. It sounds like, you know, I'm just like one room over, there's like one door. And it basically sounds like Wally's in your living room. It's like all night. It's really entertaining. Also, if you're printing other materials, some of them are supposed to be toxic. This is PLA, which is supposed to be not bad. But I think if you're printing ABS, kind of like, you wouldn't want to be near that unless it's a very ventilated area. This is me removing support. I actually spent a lot of time doing this. I usually time-lapse this part, but I think we're gonna find out really quickly if this worked or not. And I don't know if there's a better way of doing this. This is how I always do it. It's not the easiest, and you do gotta be careful because of course you could break something. I know there's some filaments meant for support. So basically the way it works is it prints all the filaments on a different support, and then that material can get dissolved in a substance. So you just go and dissolve it. So I know that's one thing. All right, oh my God, already broke it. We already have a pin fail. This should be attached there. But okay, let's look at this pin here. All right, so this should be a joint. It should move. And it's fully fused, and it broke again. It just sheared off. So I think our pins are too small and probably our clearance in between is too small. So I fear that we might have just wasted a bunch of material here. I was looking forward to putting these on the robot and like comparing it to the other part legs, but it's probably not gonna happen. Also, the whole point of removing all the screws was to simplify the assembly process. You know, remove steps, because I was having a tough time with screws. I fixed that by getting an electric screwdriver, so it's not a huge deal anymore. But these actually adds a lot of steps just by the amount of support that's here. So actually we would have to redesign the leg so there's less support if this was to actually save us any time. And then the other thing is, you know, if the pins are breaking that easy, I don't know if I wouldn't feel comfortable, you know, using that for our leg. How often are these legs gonna break? How often are we gonna have to reprint and do this entire process of removing all the support? That actually sounds like a worse design to me. I think the idea is really cool, right? What if we could just print the entire robot in one go? That would be really cool. But the execution here wasn't great. Probably need a design specific for, oh, more things just broke. Yeah, so these things are not supposed to be touched that way. All our joints are failed completely. So our clearance of, I think it was 0.1 in some spots, 0.2 in others. That has failed completely. This is any food here, which I think we're gonna mimic for the future iterations of the leg. The joints in here have also failed. We had 2 pins in here, you can only see 1. So I think overall this is a failed experiment. And I do think the idea is clever, as in like, let's see if this pin works actually. It should be working. No, that feels completely fused, man. Okay, it's rotating. It's rotating, but you can tell something's broken. Yeah. You can tell here from the way the layers are stacked that these parts were fused actually. And then we have the hip joint, which it's not rotating at all, but there is a lot of support. So, like I said, I do think the idea is really cool. Like, oh, what if I could print an entire robot in one go? But maybe we'll have to change the design. So this is the back of the hip joint. We'll have to adapt the design a little bit because this is not working. Okay, so this joint is not gonna break because it's bigger. Okay. All right. Okay, so look, this joint does work, and it's not going anywhere. Now it is a little crunchy. There's a lot of friction there. There's probably some stuff inside that needs to be cleaned up. But the fun part is I can't see it. And so yeah, you can see this is actually enclosed and it works. It's rotating as intended. And actually it feels pretty solid. So this is nice. So I think, okay, so this is a win. So this tells us that, you know, there's some promise here. Now, are we going to do this just for, like, is it worth doing it just for this part? Probably not, again, just because there's gonna be so much support here. But if we came up with a design that didn't need that much support, then I could see this working. This feels really good. I'm not gonna try to break it. I don't think I can break it actually. This is very nice. And so maybe, yeah, okay. And so what's different from here? Actually, the clearances were the same, I think. around like 0.2. We're printing on a 0.2 nozzle. That means like the opening on the nozzle is 0.2 millimeters itself, right? So printing anything smaller than that, the resolution is probably not going to do anything. A lot of pins that did break, it did look like they were fused, but also the pins were so small that maybe, maybe this one worked because it's so big that we can put a lot of force to break the parts that did fuse without destroying the part. These pins were too small. So maybe we'll have to reinforce these joints somehow for that to ever work. I'm surprised this one didn't make it either. This one is actually pretty big. This part is very dirty, a lot of support. But this feels good, man. This feels good. Yeah, so I think for the leg for now, we're just not gonna do this. It is a cool idea. It is good to know that we can do these kind of prints. So we might make use of that. But for now, we're just gonna keep going. There will be one more iteration of the leg, I think, just because things like the new food and like the new, like eliminating this the retaining ring here are things that we actually need. So those things we will have to implement. But yeah, this idea of like 3D printing the leg in one go, probably not for now. But it is cool. It is cool. I'm glad we tried that. So I was gonna end the video there. We're in a weird position where it's like we can't keep going because we don't have the parts to upgrade the electrical so the servos can move without burning down, and we don't have filament to start 3D printing the new design. So it's like, what do we do now? I wanted to do like a quick, maybe like a what do you call this? Like a post-mortem of like why our mono leg has failed. And so if we look at some of the pins that completely failed, right? So this pin here, for example, failed, and we use the same geometry everywhere. Okay, that's interesting. I didn't realize we had chamfers there. So okay, let me check this one here. Those are supposed to be fillets, not chamfers. I think fillets would add a little more clearance. Section view. All right, yeah. So that's what I had in mind, right? So if we look at this guy here, looks like on the bottom side here, there's probably somewhere around there's 0.1 clearance, and on the top there's 0.2. And like I said, we're printing on a 0.2 millimeter nozzle, right? So that 0.1, you're pretty much fusing the parts, and you can tell here that's another 0.1 here, 3.2 inner diameter, 3 divided by 2 because it splits on each side. So our diameter was also 0.1. So not surprising that these pins fused. Now let's look at another one of here. Let's look at this one here. And again, it's okay to fail, right? But we should try to learn something. So here, actually, remember how I said like, oh look, one of the ends broke. We have interference here, guys. Let me find the part. Right. So here's the broken part, right? And you can tell that it's the upper pin missing from here, right? There's two. One of them is missing. It broke, and it happens to be this one here up top, where we obviously have interference. Now, how do we have interference? Oh, wait, the camera died. Let me restart the camera 1 sec. This is what happens when you use your iPhone as a camera. I told myself I'm not buying a camera until we have 500 subscribers or something. But anyways, obviously the part where there was interference, that's what broke. Interference equals fusing, right? The slicing program in Bamboo is just gonna take that as one part. Then the other pin was fine, obviously plenty of clearance, so we made a mistake there. I made a mistake there, and I didn't catch it. I don't know how it's possible that this happened. The good part is that I recorded everything, right? So I can just go back and watch it and see what happened. So again, not enough clearance on these pins, interference issue on the main leg, and all of these pins were basically the same thing. So if one fails, I'm not surprised the other ones failed. Now let's talk about the one that actually worked really well, right? The hip. And I don't know if it worked really well because it is a little, it's a high friction fit. I would want to almost like grease it. But let's take a look here. What did we have here, right? So I mean, the first thing that sticks out, obviously, no interferences. That's great. I think a lot of this looks like a tight package here. 0.1 millimeter clearance, right? And it still worked. On the axial, 25, 2.5. 24, so that's 24.85, so that's 0.2 millimeter clearance on axial and 0.1 millimeter clearance on the diameter and 0.1 axial in both dimensions, and that worked. I do think that the fact that it's bigger helps, because if there's some spots that fuse, you can just kind of force it and it's not going to break, whereas like that wasn't true for the pins. We basically have the same clearance. Actually, axially the same clearance as the small pins. On the inside diameter, we have more clearance than the small pins. So maybe that's a lesson there to try. I do think that if we're 3D printing the small pins, we do need to reinforce them somehow. That's not enough. Yeah. And and this knee joint, obvious mistake on my part with having interference. So it almost seems like it's worth trying again. It seems like this could work. The only thing that has really turned me off is all the support, and just, you know, I would personally rather put on screws that remove support. I hate removing support, and I think it looks terrible on the end part. It just looks bad. It looks rough. You can see it. It's very hard to fix. I'm just gonna stick with the screws for now. But this was an interesting experiment. I'm glad we tried it. We'll continue to try new crazy ideas, I guess. And I guess the last thing I wanted to do today, maybe on this video, and you know, by the way, I'm going to Yosemite this weekend, so I know that filament is getting here today, but I won't be able to do significant progress until probably next week when I'm back. So that's why we're not getting started at. But the other thing I wanted to do was maybe take a look at what we designed yesterday and see if anything sticks out. Try to catch some mistakes. Well, first of all, I should really just finish the shoulders. Actually, maybe we'll do that now too. Just a cat session. Looks like some of the servos are floating here. Where are they? Oh no, that's a battery cable. Okay, I see. Let's open this part. Sometimes when I click the parts, they open. Sometimes they don't. You know, Onshape is just a mind of its own, really. It's gonna break that sharp corner there. So yeah, so maybe we cut the new shoulders, and man, I still think this belly holding the battery looks really bad. So I do want to move away from these soon. I think probably like the best solution here is to bring the legs kind of like down, right? So to the middle. Right now they're in line with this purple torso. They should be in line with whatever the middle is between the purple torso and the blue torso, if that makes sense. So we even out that thickness, and the aspect ratio doesn't look as off. That's a lot of work. So for now, let's just keep on moving. I really want to get to the software part of things. This is our switch. We never cutted the switch. Yeah, also with this thing, it's kind of hard to tell which one's front and which one's the back. Is it symmetric? It's actually not symmetric. I guess that's how we're gonna be able to tell. Yeah, and I also feel bad about this blue part because we have this giant surface here, which is redundant with this giant surface here, right? So that just adds weight, adds material, adds print time. So we could remove all of that. That's one way of doing it. What else? Oh, the other thing was we're routing small cables here, 26 gauge, 28 gauge, through these rectangle holes, cutouts. So I was thinking maybe we can add like some features to catch the wires, if you know what I mean. Does that make sense? I mean, let me just cut it. I was thinking about this last night, as I could hear Wally 3D print stuff on my living room. Yeah, so this is gonna look kind of odd, but okay, we have 3 servos, right? 3 servos each for each cutout. Let's look at my calipers here. The connectors for the servos are rectangular, 2.5 times 2.5. So if we have a hole that's smaller than 2.5, they cannot go through, right? And it's so basically, how would we do this? It will be something like here. Oh, actually, just thinking here. I was thinking something like this. My mouse is lagging. I think might be running out of battery. So we said 2.5. Actually, that doesn't matter. That doesn't even matter. So 2.5, 0.1. Okay, and 2.5. We said 3 cables of them. So 2.5 times 3 times 4. Just oh, okay. All right. Looks like this is already kind of tight. 2.5. 2.5. Okay, maybe 5. Would have to be something like this, so you can put the cable through this like little slit, and then the connector cannot go out once it's in there. And of course we gotta, man, this mouse. What's funny about this mouse is it doesn't tell you when it's low battery. You just gotta know. Okay. This might be looking a little abstract. It's gonna make more sense in a bit. Okay, and so, oh wow, it's very thin. This is a 2. My mouse is killing me. This is a 1. I thought we said these are equal. Okay, and it's not constrained, right? So constrain it to the middle of this. It's the middle of that. We will need 3, 1 per servo, and it'll be something like that, right? And so always something like that. I don't even know if we can fit 3 of these. This space is already kind of tight. right? Something like that. And then we just mirror this pattern, one on the left, one on the right. Would that be worth it? Or is that a waste? Actually, you know what's better than mirroring it? Because we can use this pin to start building it on the next side. So we don't have to mirror it. And that would actually save some material and room. Engineering, guys, it's like magic. Right, so basically this. And then here we start building the same thing. Okay, well, I do need to fix that sketch, but something like that. It's like, yeah, I thought this could be, I don't know, it's like wire management, you know? It's like, seems like minor, but having a clean package makes a big difference. Makes everything feel more refined, sophisticated. Like more thought went into it. Makes everyone feel better about what's happening. You can trust the design. Imagine if your arm had bad wire management and your veins were just all over the place. No one would trust. You wouldn't trust your arm. Be like, this arm is not good. Bad analogy, but you understand. You get what I mean. 0.1, and obviously this is all very thin, and yeah, we just had to talk about like how 0.1 is meaningless when our nozzle is 0.1 itself, right? But I think it'll be fine. I think it'll be fine. One. Almost done here. I hope this makes making sense, guys. One. Something's missing. Yeah, I guess how do we constrain? How were we constraining that before? No. Oh my god. On shape. Once you click something, it's a very sticky click, and it's basically impossible to leave it. How are we constraining? Oh, because we didn't. Oh, no, we did. How are we constraining the length of this guy? Not here. Yeah, somewhere here. Oh, I see. It's probably the length of this guy. Like that. Boom. Fully constrained. And of course, our extruded feature doesn't understand what we want to do, because on shape. Okay. My mouse is killing me. I complain too much, you know. Engineers used to draw out things. They didn't have 3D CAD. But they didn't complain. They weren't like, oh, my pen is killing me today. Alright, so that's kind of like what I had in mind. So this is 2 millimeters wide. So the connectors won't make it through because they're 2.5, and it's 5 millimeters. So this should be fine to hold the connectors from, because basically we don't want, once we route the connectors from underneath to the top, we don't want them dropping down again due to battery, because then we have to fish them out, and that would be annoying, right? So. And here we have them separated, so we know which one goes to which servo, hip, shoulder, knee, and so on. So I think it's this won't hurt. I think this is good. Now we're gonna round things up here, so everyone knows we're professionals. round it up, something like that. You need to know which ones to round, which ones not to round. That's the difference between professionals and not professionals. This is a very professional job. And now you just need to basically mirror these all around. We're getting to like the fine details here. I do fear that at some point I'm just gonna be like, you know what, we need to start from scratch. The whole thing is like, I really don't like what we've done to the aspect ratio of the robot once we added this blue part belly that holds the batteries. And I actually think the aesthetics are very, very important. I haven't talked about the mission statement, partially because I started this because I was itching to build something and there was no real mission statement. But what really gets me excited is to build a robot that resembles a living creature organism, right? That's why a dog is so good, because everyone knows dogs and everyone likes dogs. So if you can build something that resembles a dog, that's probably a big market. Even though we're not doing this, we're not monetizing these. Oh, we're missing some fillets here. Oh, I missed some. I must have missed something here. And anyways, nature has a thing for beauty. Oh, it doesn't want to apply my fillets, man. Nature has a thing for beauty. It just doesn't want to apply the you know what? It's fine. It's fine. Yeah, so things need to follow. Things need to feel right. Need to look right for you. It's part of like believing it, right? It's not like being a dog. It's not just like running around and barking. Guess look a certain way. You look, and I don't mean just like look like a dog, but also we like dogs because in part because they're so cute, you know. And this isn't cute. Anyways, I like this detail. I think that might work. We could do something similar for here, but actually no needed, because these wires are coming from the top to the bottom, so gravity is actually helping us here. We'll see how this plays out and then eventually take it from there. But yeah, I think this is good for print. I mean, the one thing that we're missing here is like we made this big cutout, but there's nothing to close it if we ever want to close it. So we could add some holes. I guess we can use screws for that. Screws, you know, not super clean. We could use magnets, stuff like that. I kind of like left it out on purpose on this iteration. But yeah, just know that did come to mind. Anyways, last thing we're gonna do here. And by the way, this is our to-do list when we started, and we've ticked everything. And I don't even know, I actually have no way to know how long this video is. But it feels like it's not that long. Last thing we're gonna do is we're gonna clean the leg assemblies. I don't understand where this is coming from. Oh, this is I see. No, we can delete these. We will change the food eventually. It's just I don't think it's like a blocker right now. Just want to make sure we don't have any. This is an Arduino button actually. That was an import. I didn't. This is our existing feed. Yeah, we have lots and lots of parts here inside our assembly, which is kind of weird coming from SolidWorks again. You add parts to the assembly. The assembly itself doesn't hold parts, but on Onshape, the assembly itself does hold parts apparently. Anyways, what we're working on today is the Servo hub. So it's called Servo hub. Shoulder servo hub. We're not assigning part numbers. I think when we first started making videos, we were saying we were going to do that. That didn't happen. This is the latest one I built. It has the physical markings, so you know which side this is. We got rid of the cutouts. There's one more thing I didn't show you guys, and it's kind of hard to show it now because we assembled a new part and it's already here on the shoulder. But this new part also weighs basically twice as much as the old part, right? Because it had those huge cutouts that make it lighter. So I was thinking like we should reduce the thickness of all of these walls, because basically these walls do very little. Yeah, I think we can reduce the thickness of all of these walls with no issues. Let's see how easy it is. So I think if we go to move face and we just, no, the other way. Well, first of all, how thick is this wall? You know, 4, right? So 4 millimeters, that's a lot of millimeters. I feel like we can bring it down to 2, and that's kind of like pushing it, but we kind of like do want to push it, right? I'm much more happier if things start breaking because we kind of like pushed it. Like now would be the time to learn those things, those lessons. And so notice I'm pushing the exterior walls inwards, not the interior ones. The interior ones made with servos. So if you move those around, you're gonna move how things interact with servos. You also don't want to reshape anything that interacts with, with any mating surfaces, basically, right? So you wouldn't touch this guy, you wouldn't touch this hole here, and looks like this wall is already very thin. So like this wall here where the servos mount, it's only 2 millimeters. All right, so now everything is 2 millimeters. We should also move the chamfers so the chamfers survive the move. Yeah. Yeah, so that already looks lighter. We can bring back the annotations here. FR. Okay, so 2.5. The only one thing I'm gonna do here is I'm gonna extend back these here, this feature, just because this surface is a mating surface, like I was saying. This does mate with there's a pin basically. I mean, I don't know if you guys already know the structure. There's like a pin that holds this thing. It's like very important for the shoulder joint. So something like that. So if we added a little bit of complexity there, but it's basically the pin that holds the shoulder, not on the servo side, but on the other side. And so we wouldn't want to like reduce that distance. And we can add just a chamfer there to make it blend in. But yeah, this looks thinner, and we still don't have the cutouts. Again, the cutouts is like my own thing. It's just like, I just don't want it to, I just don't want people to be able to see the motors from the outside. And I do realize probably no one cares. Okay, now we do gotta do the same thing for all the other. Oof, that's getting close. This one's getting very close here. Thin walls can lead to printing defects. That's why I'm looking into it. Yeah, this feels better. All right, now every shoulder is different now, so we need to redo this for every shoulder. We have here the mirror parts, but this is for the old stuff. Yeah, and so I'm gonna quickly get rid of these old parts. I think that's gonna break some mates on, you know, some of the assemblies, but all right. So we need to mirror, and then we also need to change the marking for each of them, right? Now markings, I did this off stream, but the markings are actually super easy to make. You basically find a sketch here. Actually, I'm gonna bring this to the front here. Oh, the marking could be through. We could make it a through thing. I didn't have it as a through thing, but no, let's not make it as a through. It's just a 0.5. So the markings, the way this works is when you have a sketch, there's a text feature, and basically it creates a text box and you can write in it. But you do need to constrain that text box in space, kind of like how I did it here. Just so if you want consistency, right? The text, when you write in the text, you have no control over the font size. That is controlled by the size of the text box. And so that's why I've set dimensions for my text box like this. So, you know, just a tip. All right, let's do some mirroring. So if we mirror this guy, part mirror, new, this guy, mirror plane, don't merge. Or wait, was I supposed to merge? Merge it all? New. Okay, and then I'm gonna transform these in the y-axis, I guess. Just guesstimating here. Okay. Right, so we mirror this guy, right? And so what part would this be, right? If this was front right, because this is so the hip. So this could be this. I think. Okay, let me see. This would be. Front left, I want to say. Shape. Let's see if I'm a shape rotator. That's front left. I'm a shape rotator, guys. So I'm gonna name it left hand side front, and then instead of FR, this needs to read FL. So we need to remove this face, delete this face. Sorry, remove, delete. You know, who knows? Oh my god, it's gonna be a lot of clicks. See, if only Onshape was smart enough to know what I want to do here. I mean, I don't know, maybe with AI, maybe in another 100 years, we will. By the way, I saw a really cool demo of I don't know if this is publicly available. I'll have to check. And if it is, maybe I'll share it on my next video. But there's a demo of a YC company that's building kind of like an AI tool to automate CAD, and you basically tell it what you want it to do and it does it for you. And their demo was you handed in like a 2D drawing, the kind of drawings that a supplier would give you, and they can turn it into a 3D drawing, which I thought was pretty cool. Anyways, yeah, I thought that was pretty cool. I mean, there's been a lot of situations where I think like I would have found that useful. I'm gonna take a screenshot here because I'm gonna be referencing these a lot. I also don't remember what font I used, but you know, it's okay. You know, it's okay. I'll be fine. All right. Anyways, this is kind of like how you do it. So basically, you want to define a point. You first start with a point. Point, right? So, okay, I messed that up completely. Okay, so now that we have a point, and our point is 5, our point is left-hand side base, right? So it's actually 5 plus 8. So 5 plus 8, because we're coming from the other side this time. Why are we coming from the other side? So the marking is on the front. When this is installed correctly, you can see all the markings from the front, so you can read them from the top of the robot. Instead of having to guess, oh, is it front, bottom, you know. Just those little details that go a long way. All right, now we create something here, and LR, right? Left, right, no, front, left, FL. I think this is basically how it works. And you click check, and now you have your letters. And then you just extrude this, remove 0.5, and easy as pie, right? Easy as pie, pretty easy. Now, of course, we do gotta repeat these 2 more times for rear left, rear right, and I think I can do that with a single mirror. Let's see if my shape rotating skills are up to par here. This is advanced shape rotating. Professionals only, guys. Okay. I'm of course only joking. I'm a recovering SaaS founder. My shape rotation is not maxed out yet. All right, anyways, let's see. So so this looks like a left rear to me, and the way I can tell is because this is the side that goes to the servo, and the hip is always up, so that will be left rear. The hip is, oh, that is not left rear. That would be, I mean, wait a second, shape rotation failed. I mean, that could be right rear, right there, RR. So right hand side rear, and then these by Descartes can only be left rear, and it indeed is left rear. So, you know, shape rotation, get in there. Some work to be done. If I print these, start printing these before the new filament gets here, basically that means that the colors are gonna be inconsistent. I know it's gonna look a little bit ugly, and I'm a bit mindful of that just because, like, I think, again, going back to the whole build things that are nice, inconsistent color matching is not nice. I just think it will be cool because it's a really nice way to track progress, and you can tell, oh, that part is green. Wow, we've been using that part for a long time. Someone was also telling me that I should stop naming the videos part 1, part 2, part 3, because people don't like watching that. And you know, I was all like, oh, but I'm not doing this to get views, you know. And there's some truth to that. I'm not really doing this to get views, because if I was doing this to get views, I think I would be posting a different kind of content. I don't think this is very mainstream content. Wait. Oh, yes. So there's some truth to that, but also, so it's this side. What I was gonna say, yeah. Also, I mean, I obviously wouldn't mind getting a ton of views, you know. It's just that And I was thinking, like, just thinking back to like myself in high school, even back then I was already making YouTube videos. That's a different channel, you won't find in this channel. Very cringe. So I think I always kind of like wanted to do YouTube, and this was many years ago, guys. This is before it was cool. This is just me thinking like, oh, this is cool. This is before, you know, YouTubers were celebrities basically. And so I cannot say, oh, I don't care if no one watches it. I do care. I just think that this is not the kind of content that the masses will consume. And eventually we will get there, right? Like once we have a lot of robots that are really cool and do cool things, then we can generate content that more people are willing to consume. But for now, I think it's much more valuable to basically have less viewers, but who are, you know, more into it and maybe have a technical background, and, you know, can provide feedback and comments, and maybe in the future we could even build something together. I think that would be more valuable. So in a way, I'm trying to optimize for, and this could sound bad, but I'm trying to optimize for quality of viewership versus quantity of viewership. And I don't know if I'm doing a good job at it, but I think if I had to, you know, lay down a strategy, it would be something along those lines. I think that would make sense to me. Okay, this is the last one. I don't know, what do you think? Did that make sense to you? I mean, if it made sense to you, it has to be right. Coincident. All right, and this is left, right, left rear, left rear. No, we have FR for front right. This should be rear left, or RL, rear left, front right, rear right. Wait, front right, rear left. Yeah, I mean, not super clear. Rear left. Reinforcement learning. It's kind of like, it's like a secret code. No one's gonna know what this means unless you build this. All right. So those are all the parts. Front right, front left, rear right, rear left. And now, you know, we could print this right now. Actually, let's do that right now. Let's print them right now. And while we also, I just want to flex my bamboo. We're gonna load the camera here, make sure the bed is nice, and there's something in the bed now. Okay, bed looks nice. I guess we're also gonna clean the cat. You know, clean the cat. Now, what would you do first? Would you clean the cut first? Or would you start printing? You would obviously clean the cut first. What if you catch an error? That makes a lot of sense, right? You should clean the cut first. Yes, okay. But no, we don't do that this way. It's because we trust that we made no errors, of course. We're professionals, guys. Well, let's slice it and see how it looks. Yeah, so we did introduce another support point there. Overall, very nice to see no support on these sides because we removed those overhangs, and those walls are looking thin. That's nice. I like to see that. I am curious if the walls are so thin that it's all infill, or those are all infill. So one thing I would change here is the thickness for walls. So right now I think it's set to, let's see if I can find this somewhere. Strength. Wall loops 2, right? So if we set it to 4 and we reslice it, Yeah, you see now these walls are solid. There's no air gap there. So that could be interesting. Well, actually, okay, so we have 4 hours. So basically 1 hour per shoulder. And if we set it back to 2, what happens to that print time? 3. So we're adding half an hour if we want to make more solid walls. I don't think we need it. Also, this is kind of like a paint that's support from the inside. And I was wondering, what happens if we say support on build plate only? One of the issues with having these, it's like when you're printing a lot of parts on the same plate, you cannot specify settings on a per part level. All the parts that you print need to have the same settings. See, I was under the impression that circles didn't require support because, you know, basically it's self-supporting, it's like an arch. But okay. I think this is fine by me. It's gonna use 127 grams of filament. It's gonna cost us $3. There's no, I don't have a good way to tell if we actually have enough filament other than like, you know, to try it. So let's just try it. Like the filament roll is at the point where basically all the markings on the filament thing, it's under all of the markings, but it's not so low that I can already see the inside of the filament barrel. So whatever that means, that's where we are. All right, and the last thing is just, we're just gonna, you can tune out by now, it's just, we're gonna clean up the cat to include the new shoulders we just added here. So now that every shoulder is different, this means that we're gonna have to have a leg assembly for every single leg. So it's just gonna be rear, right leg assembly, and then this is gonna be rear, left leg assembly. As you can see, the leg is already rebolting, already it's breaking apart. Say no, don't do it, but we have to do it. So we're gonna insert our new servo hub. This is the rear right, and I don't know, there's an origin, but nothing is really following this origin. So an origin is like on the Cartesian plane of things, the 0, 0, 0 point. This is the origin here. Normally you use that to, you know, to kind of like, you set that to something representative, something that's important, maybe like the hip, the center of the hip, or something that's very important. In this case, it's absolutely nothing. It's just floating there. It's like not a good practice. Now you can see those, you can hear those noises. That's actually the printer getting to work. So it looks like these servos drive a lot of the mates in here. So we're just gonna do a lot of mating, and this is a bit tedious because, yeah, we do have to do these 4 times because there are 4 different leg assemblies now, and so we're gonna be here a while, but I'll try to keep talking. Yeah. By the way, guys, something that happened today, not super related to these, but just if you're in tech, kind of interesting. WorldCoin just announced their new, had a product announcement or something. It's like, that's Sam Altman's project, where it's like a on-chain human verification protocol thing where they scan your retina to prove that you're human or something like that. So they made a bunch of announcements around that. They have a new retina scanner or something like that. They said that, I think it's like 1 in every 3 people in Buenos Aires, Argentina, has already scanned their retina, which sounds insane. First of all, I'm just curious, like, why Buenos Aires? Why Argentina? why are they launching in South America? Seems like is crypto adoption higher there or something? Like totally missed that. Anyways, that stood out to me. A lot of the stuff was like in my mind is like, who's asking for these? Because like I think the underlying utility is like, oh, we can prove that you're human, you're not a deep fake, you're not an AI, and I think that's useful for sure. But the people that's useful for, that's a small group of people right now, right? It's like if you're a celebrity, a politician, some sort of leader, that's probably useful for you. But for the general population, I would say kind of like not useful. Now, if you're offering free tokens for people to scan their retina, well, that's a different story, right? It's like basically free money for you to take a picture of my retina. I don't know, maybe I'll do it. There was a time where I was very optimistic about these things, and I would have been like first in line. But I had an experience with 23andMe. 23andMe basically, they basically map your DNA. So you send your speed sample to them, and they map your DNA, and they tell you things like, oh, what diseases you're prone to, and stuff like that, and who are like, they help you find family and all these things. You can do a lot of things with someone's DNA. But there was always a concern of, oh, what happens if the company ever goes under? What happens if where is this supposed to go? Yeah, what happens if the company misuses the basically your information? What happens to your privacy? Because they have your DNA. They know, like, it's kind of hard to hide that. And at the time, this was many years ago, so at the time it was like, oh yeah, kind of like you're sounding paranoid. But if you look it up, 23andMe is actually basically going bankrupt now. So a lot of these concerns are real, and I haven't had any repercussions yet. Like, I haven't been, like I said, I did do it. As far as I know, my data is still safe, I think. I did use a fake name, of course, because I was a little paranoid even back then, but I guess it taught me a lesson of like thinking more long term with things like data privacy. And we kind of like, sometimes it's hard to imagine how the world's going to change. At the same time, if the AI has taken over and you're the AI listening to this, I don't want you to think that I'm anti-AI. I'm an ally. Okay, it's not. This looks about right. We're probably gonna skip on some fasteners here, just to keep things moving. Let's see. Don't need this. Don't need. Removing parts always feels good. Anyways, I think WorldCoin is worth checking out. 519. And maybe Buenos Aires is worth checking out and see what's going on down there with crypto. Okay. Okay, it looks like something's still broken, right? See, it's interesting because we have an origin, but we don't have origin planes. So a point in space can be defined by 3 planes intersecting. And so normally in SOLIDWORKS you would have that, but here you don't have that. And obviously there are planes, because you can see the planes here are defined, but let's see, can I set origin? Can I use the origin? I'll say fastener. Looks like I cannot mate things to the origin. On-shape place fixes. Yeah, I'm gonna remove these things. We don't need these things. It's not useful to have these things. What is this? Don't need. Don't need. Okay. I think this, yeah, I think that's supposed to sit on the servo horn. Like that. Right? And then this guy sits, I don't know, I guess the retaining ring sits on the servo horn as well. I forget. Let's try that. Section view. Whenever I criticize anything new, like work coin or anything like that, or I'm like, oh, be cautious, I just feel like that's a losing position, you know? It's like, it's hard to argue against technology like that. And if the forces that will, like, you know, with enough resources, they'll make it happen. So I think it's always, I always prefer just to be very optimistic and embrace these new things. And I know, you know, other people feel different about it, and I think that's completely fine. Cylindrical. Let's try. Can we do cylindrical to this point here? Oh, oh no. Looks like we can't use the origin whatsoever for anything. So can I use this origin? Mate. Okay, see, it did it. It just did it on the wrong axis. But it tried. It's getting better. Let's try. Man. This is not giving me the control that I want. I mean, that would be the top. Oh, let's try it. So this is the top plane now. This isn't actually the top. Oh, and so actually something broke. Okay. Well, at least it's a little more organized, right? At least it's like squared up. I'm just gonna like fix this in space. No, man. Yoke servo, you can't do that. Something like this would be the natural position. And so now we can go to our top assembly here, and it will be all messed up. And we can actually, none of these options are great. I guess this must be, why is it locked in a position all the way up? So we don't have positions anymore. Unlock. No. What do we do it? Okay, so we gotta go back and set a position here. I'm just gonna set this position here. Chilling, apply name position, update name position. All right. Yeah. Okay. So that's more like it. And this one is obviously, it's an easy mate. It's like cylindrical here. This is that pin we were talking about earlier, and then here. Oh, we still have the old servo horns. We don't need those anymore. Now we have our built-in servo horns. Printers sounds like it's printing now. It's pretty cool having the camera here. You see these kind of like hairs going up? That's not good to have. I've never been super into tuning 3D printers to get the perfect print. That was actually what got me into bamboo, hoping that I wouldn't have to do that. So I hope I don't have to do that. Anyways, that's one. This one here, we just need to delete these since that's gonna be front right now. Let's see now, leg looks a little cleaner. I still think, yeah, leg design can still be improved, but the legs haven't broken yet, other than the shoulder, which we just fixed. So, I mean, next we could do front right leg assembly. One of the pains of having all these assemblies for like, front right, front left, and so on, is that if you change anything on any leg, you're gonna have to go and update all of them. So make one change, apply it 4 times. Not exactly fun. Now, SolidWorks has this feature where in an assembly you can replace a part. I don't know if oh yeah, you can do it here too. So you can replace it, so you break less mates. So this is right hand side front. Oh, that was kind of useless actually. Yeah. Anyways, that didn't do what I thought it would do. I thought it would like carry over the mates and be nice and all that stuff, you know. First I'm gonna apply that same cylindrical mate from the hip to the origin, which doesn't actually do what I want it to. Oh my god. It changed the axis. It just does whatever it wants, guys. Onshape has a mind of its own. Maybe we can all learn a lesson from Onshape. Anyways, here we come, more mates. As always, the hip goes up. That's the one thing I've remembered after assembling these things so many times. Hip goes up. If I have one thing to take away, the hip goes up. So I know. Alright, we just keep working our way through these things. I was also thinking of doing a Midjourney video, and I was also thinking of doing some flying my drone videos. I built a drone a while back, and I just built it. I bought a bunch of really nice parts, and I just never flew with it. I never learned to fly. Flying is like more complicated than you'd think. In my opinion, at least, flying is more complicated than I thought. I'm not like flying like a DJI or something that basically just flies on its own. I'm flying like, what is it, a B, what's that flight controller? B, flight controller. Speedy B. So Speedy B is like basically a flight controller meant for, I think, racing and acrobatics and stuff like that. And so it doesn't hold its position well. You gotta do that. Versus like, you know, in the past I've flown Pixhawks. Pixhawk has like, you know, GPS and like airspeed sensing and all this stuff, and it can hold its position really well, and so you can do things like photography. With Speedy B, well, I mean, that's, I guess the name is proper, Speedy B. You just gotta, oh, okay, oh my god. Yeah, Speedy B, you gotta be speedy. It moves very speedy. It doesn't hold its position. It just wants to go. And so, yeah, you kind of like gotta be a good pilot, which I'm not. I also had this idea for, and this is gonna sound very crude, but I was looking at some footage from the war in Ukraine, and I'm gonna get canceled. Obviously, drones are playing a very strong role in that battle, in the battlefield there. And I was seeing like soldiers basically have techniques to dodge drones because the drone basically has a explosive attached to it and it dives to get the soldiers, which sounds terrible. And then some soldiers dodge the drones sometimes, and it's like, obviously, you know, that's a terrible thing. But I was also thinking, you know, outside of the realm of war, with no explosions or anything, in a safe environment, I was wondering if that could be a sport. As in, like, you know, we have dodgeball. Could we have dodge drone? I think so. Is dodge drone the biggest opportunity you can pursue in robotics? Probably not. Are there things more important than money? Yes. If we want to live in the future, our culture also has to evolve, right? And sports are part of culture. It's like, if we're still kicking around balls in the future, are we even living in the future? We should, future requires future sports, future modes of transportation, future foods, future culture, future politics, future economical systems, all kinds of future. So yeah, anyways, I haven't found people who wanna get hit by my drone yet. I guess the first step is for me to actually learn how to fly. So then I can go and ask people if they wanna, if they'll let me hit them with my drone, because sports. I need to figure out how to actually make things to the origin. There's gotta be a way. Printer's going crazy. Anyways, I don't know if there's a way. You kind of do roughly, you're gonna do it like that. Fix it. Alright, we're almost done. We're halfway through, basically. Let's see. Put this here. It's funny because I remember some mechanical engineering jobs that ask you to have like, oh, it's like 10,000 hours of SolidWorks and stuff, or CAD or stuff like that. I'm pretty sure I crossed 10,000 hours in my during just undergrad years. By the way, not all hours are equal. If you're doing hours of like, you know, mating things together, it's not the same as if you're doing hours of modeling complex surfaces, like A-class surfaces for an automotive studio in CATIA or something. This is all CAD. It's just not the same. There's levels to this, as with anything in life. I don't know if I already told this story. Like, I did go to Waterloo, and it's a school in Canada. It's an engineering school in Canada, and the school is known for its co-op program. So co-ops are basically internships, and so this school requires you to complete, I think, 6 internships in order to graduate. So it's not just go to class; it's also complete these internships to graduate. And so every term you have, so every year you have either 1 or 2 study terms, and then 1 or 2 work terms. And so you don't have any vacations. You're either studying or working. And because of these, the degrees take 5 years. So for 5 years, you're either studying or working. And so it's a very interesting dynamic. There's no vacations. I'm shocked when I guess by now I'm not shocked. I just accept it. But a lot of people, when they go to college, they go places in the summer, vacations and stuff like that. We would go nowhere. We would just you would just go wherever your co-op or internship is. Now, luckily, some of these internships were in nice places. For example, California, right? So we were in Waterloo's in Canada, in Ontario. It's like a small town. Not a lot to do, in my opinion. I think it's a nice town, but it's a small town. And it's kind of like cold, and it can get a little bit depressing. But then if you are good, and you gotta be good because it's very competitive, you can get to go do your internship somewhere nice and warm. And so there's this whole subculture of Cali or bust, basically make it to California or rip. I don't know if Waterloo's people are still doing this. Man, I'm doing the thing where I click and Onshape does nothing. Super frustrating, Onshape. Anyways, we would have this very competitive culture. I was like super lucky to make it to Cali. So basically I had 2 internships at a manufacturing company in Ontario. Called Skyjack, owned by Linamar, a big automotive conglomerate group. Skyjack makes scissor lifts, booms, and telehandlers. So basically, kind of like this heavy-duty construction equipment. And I was basically a cat monkey for one of the design teams, and we I did 2 internships there, like I said. So I worked first on, we developed 4 different telehandlers, basically the same telehandler with different slightly modified chassis to handle different loads. And then I kept going back, and we developed some different booms. So this is what a boom is. I feel like most people don't know what a boom is. Maybe I'm even pronouncing it wrong. Boom, telescope. So this is what a boom is, right? So you take these to construction so you can reach somewhere very far, very high. It's basically a better ladder, and there's articulating ones, there's electric ones. So I got to work on these kind of things. And then Skyjack also makes scissor lifts, which is exactly what it sounds like. That's a scissor lift. So it was a cool place to work. My first time stepping in a factory. I was very naive. I was fresh out of high school. And it was very interesting. And then that was in Cali, that was in Ontario. But I was just so excited to be able to work somewhere. That was my first time having a job anywhere. What is this? And so I was super excited. I didn't care, you know. I don't know if people think highly of Skyjack or not. I was very excited, man. And just being able to build these things. These machines are cool because they're huge. They're huge. It's like some of those booms are over 100 feet. And so they look like, I used to tell my manager, it's like, this is the closest we have to dinosaurs in this day and age. This is like working on a dinosaur. I thought it was very cool. And these are all very thick steel assemblies, weldments, very thick weldments. You know, it's a rough industry where it's like, you know, costs need to be low. Oh wait, what's going on here? Rear left. Rear left. This doesn't look like rear left, right? It's like, should be... Oh, I assembled this wrong, right? Yeah, rear left should be like this. Oh, I guess it could be assembled like this too. Oh, I see. I didn't follow my own markings. Anyways, where I was going with this was that oh, what the heck? I need to figure out which mates to break. I wish I could just click a part and it'll show me all the mates it has. Anyways, where I was going with this is like, yeah, first of all, I think even the jobs that are not as prestigious as like working at a company in Ontario manufacturing, you know, construction equipments, they're not an industry leader or anything like that. They just do their thing. I thought that was a great experience. Like I said, you need at least 6 internships to graduate, so we have internship terms. Now, before this wasn't my first, this was my first job, but it wasn't my first time trying to get a job. The previous work term, I actually went unemployed. This can happen. You can get unemployed if no one hires you, if you don't convince anyone to hire you. And what I did for that entire term was I would just go to one of the computer labs on campus. I would open SolidWorks and I would just CAD whatever I thought was cool. It was mostly airplanes at the time, but this wasn't me like trying to copy an airplane that exists. No, this was just me like, it's kind of like when you're a kid and you're drawing things out of your imagination. Except I wasn't a kid. I was like, oh wait, what's going on here? Except yeah, wasn't a kid. Wasn't drawing. It was CAD. I was in university. But I did that for a while, and I got really good at CAD. You know, I don't want to say like, oh, I was the best in my class at CAD. I think I probably was, just because I spent, you know, an insane amount of time. But anyways, that really helped, and then the next co-op I was actually able to get an internship at Tesla. And this wasn't the Tesla that you know, right? This wasn't Tesla here trading at $200. This was Tesla trading at $10. You know, it's like when I would tell my parents like, oh, I got an internship at Tesla, they were like, what is that? You know, it wasn't as cool as it might be now. but I was just excited to be able to work somewhere cool, because Tesla was in the Bay Area, it was in California. And again, Waterloo had all this culture of Kali and bus and stuff like that. If I had not gone to Waterloo, I don't think that would have registered. I don't think, you know, it's like, oh wait, why do I want to go there? Oh, it's nice, I guess. They pay good, sure. I feel like other places can pay good too. Anyways, that's kind of like my story. I think we fixed this now. Yes. I think it helps a lot to kind of like think back of like who you were. Coming out of high school feels like a very special time. Like I said, in high school, I was already making YouTube videos. It wasn't cool, but I thought, you know, there was something to it. And the other thing when I think back, it's like I said, like in university, even before I knew how to build anything, I was already trying to build things. When I was unemployed, I was like just thinking of like, oh, how can I design an airplane? Just like literally catting it in 3D. There's a whole story of me building submarines in school, which I will get to it one time. Or even just, you know, telling my manager that, oh, it's so cool that we get to build these dinosaurs, you know. It's like just it's like making YouTube videos and building things. These things have been constants in my life. I've always been into these things, so it's like this is it's kind of like what I'm into, and that's why we're here. I mean, as in like this is why I'm doing this right now. All right, last leg. Replace left hand side front. Of course, none of the mates carry over. Fantastic, great job on shape. All right. Printer going crazy. Have you guys seen that TikTok meme of like, you know, Trump's voice saying like they're eating the dogs and stuff like that, and people are making all kinds of memes? I wanted to make something like that, and like with this dog, you know, imagine this is in the oven and it's like just moving around, and it's like then the audio is playing. They're eating the dogs. Could that go viral? I do think like using these robots to create content is like something that I'll be very much into. So as soon as we have the electronics running again, I think I'll start doing things like that. That noise, by the way, I had the Rockefeller book on top of the printer, and it shakes so much that I just bumped it to the ground, but nothing else broke, or nothing broke. Okay, that's the last leg. Chilling. A lot of broken things here, broken mates and stuff. I'll probably just delete all this broken stuff. It's broken already, right? So it does nothing. This is probably the cleanest the cat has ever been, ever. Front left assembly. Come on. Oh no. Oh wait, oh yes. Even with the markings, sometimes it's hard to tell if the legs are correctly positioned. right here. Yes, that's it. This is what we're building next week. Next video. So I'm gonna finish it. I'm gonna leave it there. Do you guys want to see where the printer's at? So this is where we're at. We're on layer 13 out of 283. We are 17% done. It's a 3.5 hours print. So we'll finish today. I'm not gonna assemble it today because we do gotta disassemble the entire robot anyways once we print the other stuff. But I think that's where I'm gonna leave it. That's the robot. This is what we got done this week. We explained the electrical improvements, repackaged all the electronic stuff. It looks much neater, right? The torso, you know, we added a belly. I still hate it, but all of that is new. When we tried to 3D print it in one piece, didn't go great. We did learn some stuff. The stuff that worked pretty well. So that's cool. And now we're just waiting on Jeff Bezos to deliver us some new filament, some new wires, some new parts, so we can actually start building these. I will of course start printing these as soon as we can. And so next video, I'll want to have this thing built, and I want to be able to move everything, all the legs again without catching on fire. And that's when we can start to work on the software stuff. So what we haven't done, yeah, we've moved the legs, but we haven't actually taken a step forward yet. So I think that's like the next big milestone. Take a step forward. Thanks Tom for watching, means a lot, and I'll see you next time. Alright, so I know I already finished this video, but I was just editing the video and I got this notification from Bamboo, which I thought was like funny. It says we've run out of filament, right? So that's where the print is, and we've run out of filament. So if we go here and we go see it, it has stopped, and indeed we have no filament left. So we could wait. I don't know how, this is the Bamboo's poop. We could wait. I don't know how long until we get filament, or we could just like scrap these parts so they're not two colors, and we'll print it next time. So I think I'm gonna go do that. So yeah, I just thought it was funny. Really cool to see Bamboo, you know, kind of like is smart enough to tell when this happens. So I just want to show you guys that. Seriously, get a Bamboo. These things are really cool.